What's up, guys? In this video, I went through my back catalog and found the top examples that I want you to know to be able to understand analytic trigonometry, basically dealing with trigonometric identities. So we're going to talk about how to simplify a trigonometric expression using your trigonometric identities. We're going to talk about verifying identities, and we're not just going to do it talking about it. We're going to be doing multiple examples. And then we're going to get into applying the sum and difference formulas, as well as the double angle, as well as half angled formulas. And we're going to do this to apply, again, by simplifying, verifying, evaluating, as well as solving trigonometric equations. So all of this content is all included in this video. And I can guarantee you by the end of this video, if you go through all of these examples, you are going to have a better understanding of analytic trigonometry. I look forward to seeing you at the end. Cheers.
Welcome. So how do we simplify trigonometric expressions, and what is really going to be kind of the process that we're going to want to follow? Well, you know, very similar to what we learned when we first started doing like order of operations to simplify numeric and algebraic expressions. We're going to be using a lot of those properties to go through this. And to simplify trigonometric expressions, what we're going to want to do is take our complicated expression and simplify it to its, simplest form. Usually trying to written out in either as a form as a number or in its simplest function of either, one or two functions, either, combined or as least as one expression. So to do that, there's a lot of things that you're going to have to start looking into. And I want to kind of go through a couple main points that I see in algebra that I want to make sure students remember as far as how we're going to apply them in our trigonometric expressions. The first one is our reciprocal property. If we have x over y times 1 over x, remember we can rewrite that as x divided by y over x. Therefore, the x's are now going to divide to 1, and I'm just left with 1 over y. So it's very important, especially when we're looking into multiplying rational expressions, or we just have one rational expression. We always want to look for that opportunity to be able to divide out our trigonometric terms so they can equal 1. This also comes up when we have maybe complex. So let's say if I had x divided by y divided by z. All right? So a lot of times what we want to do for this one is, again, look for our reciprocals. So if I have x divided by y divided by z, I can multiply this by 1 over z. Again, by multiplying this by my reciprocal, that divides to 1. And then I'm left with multiplying by the reciprocal in the denominator and the numerator, where my final answer would be x over y times z. All right, so those are some very important skills when dealing with fractions and your reciprocals. But that's not the only take that we're going to be using for simplifying our trigonometric identities. One thing we're also going to go through is factoring. You need to remember how to make sure you can factor the difference of two squares. Make sure you can factor by using our AC method, or just be able to factor a regular trinomial when our coefficient of a equals 1. They're going to come up. We're going to want to go ahead and use them. And what we do is when we simplify or when we use our factoring, the main important thing about simplifying trigonometric expressions is looking for the opportunity to use our identities. And again, the identities, which have previously been given to you guys, have a reference sheet. You're going to want to use those identities to substitute them into an equation. So therefore, you now produce maybe a fraction. So for instance, if I had like tangent of theta times cosine of theta. Well, if I wanted to simplify this, I can use my quotient identity to say, all right, well, let's rewrite this. Let's get this into some fractions, so maybe then I can simplify this out. So I can rewrite the tangent as sine of theta over cosine of theta times cosine of theta. Now I have a similar operation like I had over here, where now the cosines are going to divide out, and I'm just left with one trigonometric term of sine. So that's going to be very important when you're looking for these. You're always going to want to be using, think about the main ones that I would like to say is your quotient, reciprocal, or Pythagorean. Because I can give him the big P because he's a big guy. All right, those are going to be your main identities that you're going to be using. You're going to use cofunction. You're going to use even and odd. But those are going to be your main functions that almost on every single problem you're going to want to apply. And you're going to want to substitute. And the great thing about simplifying expressions is it's all about just trying. See how far you can get, try something, and if it doesn't work out, try maybe substituting in a different identity and see where it's at. There's not always great right or wrong answers. But one thing I do want to talk about for you to look for when you're simplifying your trigonometric identities is looking for these terms of sine squared of x, cosine squared of x, or tangent squared of x. All right? When you see any one of these trigonometric terms, what I always think are actually even their reciprocal identities. All right? There's not a lot that we use with these true identities when simplifying a trigonometric expression. So whenever I see any of these terms squared, I automatically think I'm going to try to replace it with the Pythagorean identity. Now, not always is that the best solution or the best thing to do, but a lot of the times that is going to get something moving where you're going to be able to finally simplify your expression. You're finally going to get maybe the same terms on the numerator and denominator that you can divide out. So look for those opportunities for when you have these functions that are squared. Look to try to apply your Pythagorean identities to substitute in those values. Also, try looking for opportunities to create a sine squared, cosine squared, and so forth. For instance, if I have like 1 over cosine of theta minus 1, well, if I go ahead and simplify this, I don't know, let's do sine or something. I'm just totally making something up. But right now, there's really nothing I can do to kind of simplify that. However, if I go ahead and multiply my denominator by cosine of theta plus 1, now what I've created in my denominator is cosine squared minus 1. And we know that sine squared plus cosine squared equals 1. That is your trigonometric expression, right? So now, by go ahead and rewriting this, I can now replace this in my denominator because I have sine of theta times cosine of theta plus 1. I can now rewrite cosine of negative 1 as negative sine squared of theta. Now, how that's going to affect the rest of that problem, I just kind of made that up, for instance. But then you'd be able to delete out a sine. Then you'd have a cosine over sine, which you can convert to a tangent. And then you might possibly have a trigonometric identity in terms of tangent or cotangent. So you just got to start looking at the box. And I would just say, in general, when looking through these problems, is just going to start trying things. Try it, see how far you can get. Make sure you're applying your identities, because that's pretty much what we're going to do, is applying your identities and your algebraic processes. If you see an opportunity to add or to add, you got to get common denominators, right? That was actually another one. If I have 1 over 2 plus 1 over 3, to add those, we got to make sure we have common denominators. So I'll multiply by 3 over 3 and 2 over 2. Then I can now add this as 3 over 6 plus 2 over 6. All right? So when you're looking at adding, make sure you remember those algebraic processes. Take advantage of your opportunities of multiplying, dividing, adding, subtracting, especially factoring, and as well as trying to get to your Pythagorean identities so you can replace them and then simplify. So here we go, ladies and gentlemen. I hope that helped you for how do you simplify your trigonometric expressions. Thanks. So before I started doing this, and without talking, does anybody remember, or maybe I didn't say it for you guys, does anybody remember what I said for you to look for whenever you see a sine or trigonometric function squared? The what? Pythagorean identities, right? Anytime you see a trigonometric function squared, automatically think to yourself, all right, I might want to or might need to use the Pythagorean identities. Same thing like whenever you guys see a right triangle. You can apply the Pythagorean theorem, right? And that's something you guys should always think about. When you see a right triangle, ooh, I know that Pythagorean theorem can work out. Well, when you have a trigonometric function squared, there's any other identity, it's not going to apply except for, or a couple of them will apply as far as like thing. But the main important thing to get rid of that squared we're going to want to look for is by using the Pythagorean identities. So let's go and write out the ones that deal with sine squared and cosecant squared, right? I gave you guys that little quiz to kind of test you, see what you have. So you need to know that sine squared of theta, or we're dealing with x, so x plus cosine squared of x equals 1. And then for the cosecant, we know that 1 plus cotangent squared of x equals cosecant squared of x. Okay? So you have to know those two Pythagorean identities, all right, to apply them. So these are the two identities, but is that what we have up here? No. So what we're going to do again is we're going to transform our Pythagorean identities so they can fit into what we're looking for. This says 1 minus sine squared of x. Well, here I have sine squared of x plus cosine squared of x. So what I showed you guys last time, I don't need to explain this. I can easily tell you this, show you guys this without talking, is I'm just going to, what happens if I subtract sine of x on both sides? Is my equation still going to be the same and equivalent? Yeah, I'm not doing anything. I'm just using the subtraction property of equality. So my equation is still going to have the same value, or it's still going to be equal, but now it's just written in a different format, right? All right. Then I can do the same thing here. What about if I just subtracted 1? I'm not changing the equality of the equation. All right. So now you guys see I have the numerator right here and the denominator right there, right? But what we want to do is we want to simplify this. So what we say is, since this equals that, and since this equals that, how about we replace what they equal into our function to see if we can simplify it? Does that kind of make a little sense on what I'm doing? All right. So since 1 minus sine squared of x is equal to cosine squared of x, let's put that up there all over the cotangent squared of x. Okay? So now, so far, this looks pretty simplified. This is, simplified down there. But let's see, can we even simplify it even further? All right? So then we look at, well, how about let's try to get rid of a fraction down here. Let's try to get rid of this. So if we know that cotangent, what is cotangent squared of x going to equal? Well, again, we can apply the quotient identity. The cotangent squared would be the same thing as cosine squared of x divided by sine squared of x, right? Because cotangent is cosine over sine. So if it's squared, that just means it's cosine squared over sine squared. All right? If it was cubed, it would be cosine cubed over sine cubed. So let's go and replace this over here. Let's see what happens. So if I have cosine squared of x divided by cosine squared of x divided by sine squared of x. And then, ladies and gentlemen, what have we been doing so many times in this class? When we have a fraction on the bottom of another fraction, how do we get rid of the denominator? We multiply by the reciprocal. So you take the reciprocal of this, which would be sine squared of x over cosine squared of x. We multiply by the reciprocal because any number multiplied by a reciprocal multiplies to 1. Whatever you do on the bottom, you multiply on the top. So now I'm multiplying sine squared of x divided by cosine squared of x. So therefore, what this really looks like, I know I kind of ran out of room, but this really looks like this. So therefore, this is actually in the numerator. So you have a cosine squared in the numerator and a cosine squared in the denominator. So therefore, they're actually going to divide out to 1, leaving you with a sine squared of theta. Or of x, I'm sorry. Okay? Welcome. So what I have is the cosine of x divided by 1 plus sine of x plus 1 plus sine of x divided by the cosine of x. So when looking at a problem like this, the main important thing is we see fractions. We're like, oh, I hate fractions. I never want to deal with fractions. And we just need to go back and think about easier fractions. How do we add fractions? We have unlike denominators. So, let's say we have, 3/4 plus 2/5. So when multiplying or when adding fractions, we need to make sure that we have the same denominator. Therefore, I need to find the least common multiple between 4 and 5. Well, the least common multiple between 4 and 5 is 20. So to get to 20, I need to multiply by 5 on the left side and 4 on the right side. And then make sure that I multiply the numerator and the denominator by the same term, so I'm going to have like terms, or like fractions. So therefore, I have 15 over 20 plus 8 over 20, which ends up giving me 23 over 20. So for this problem, I'm going to do the same thing. However, it's a little bit more difficult to look at these and say, what's my least common multiple between 1 plus sine of x plus times cosine of x? Well, what you notice is I multiplied my two denominators pretty much by each other to find my least common multiple. That's not always going to provide you least common multiple when dealing with numbers, but it's a great way to always find a multiple when dealing with trigonometric terms. So that's exactly what I'm going to do. I'm just going to multiply by my other denominator on both sides. So I multiply by cosine of x on the numerator and denominator on the left side, and then I multiply by 1 plus sine of x on the right side. OK, so now what I'm going to do is I'm just going to distribute property through. So cosine times cosine is cosine squared of x. All over, multiply, distribute this through. I'm going to have cosine of x plus cosine of x sine of x plus, now here I'm going to have a binomial times the same binomial, which would be a perfect square. Therefore, I'm going to have 1 squared plus 2 sine of x plus sine squared of x. Now, if you want to do FOIL to check your answer, that's perfectly fine as well. And then I notice my denominator here is going to be exactly the same. As I distribute property through, I have cosine of x plus cosine of x sine of x. And it's very important that we notice and we make sure that we have the exact same denominator. So now that we have the exact same denominator, what I can do is I can combine my numerators together. So now I have cosine squared of x, and I'm just going to kind of rewrite terms next to each other, times sine squared of x. Since we all have addition, it doesn't, we can commutative property, we can use that, plus 2 sine of x plus 1. And this is going to be all divided by cosine of x plus cosine of x sine of x. OK, so now what we want to do is see, can we simplify this any further? Well, I notice I have cosine squared and sine squared, so therefore I'm going to look into the Pythagorean identities and see what I can do to rewrite those. So sine squared plus cosine squared equals 1. So therefore, to solve, let's solve for sine squared. So I'll subtract cosine squared of x on both sides. Therefore, I get sine squared of x equals 1 minus cosine squared of x. So now what I'm going to do is I'm going to plug in 1 minus cosine squared of x in for sine squared of x. The reason why I want to do that is because I want to see, is this going to cancel out or anything? So let's check it out. When I have cosine squared of x, now when I add in 1 minus cosine squared of x, so when I plug that in for there, you notice that now I'm going to have a positive cosine and a negative cosine of x. So plus 2 sine of x plus 1. And then again, this is all over my denominator, which is cosine of x plus cosine of x sine of x. OK, so now looking at this, I know that these are going to subtract to 0. I have plus 1, which is now going to give me 2. And then I'm going to have 2 sine of x. So therefore, my final answer is going to be 2 plus 2 sine of x all over cosine of x plus cosine of x times sine of x. And one thing I look at I might want to do here, let's see if I factor out a 2. If I factor out a 2, I'm going to be left with 2 times 1 plus sine of x. And then over here, if I factor out a cosine of x, I'm going to be left with 1 plus sine of x. Well, therefore, by noticing this, what I notice I could simplify it a little bit further, right? So I'm not exactly done here. So by factoring out a 2 and then factoring out a cosine, you notice that I have now, again, multiplication. So I can now divide these out to 1, which leaves me with 2 over cosine of x. Now, rewriting this as a non-fractional form, I could rewrite this as 2 secant of x. So there you go, ladies and gentlemen. That's how you simplify by adding 2 rational trigonometric terms. Thanks. So I have cosine squared of x divided by 1 minus sine of x. All right? And one of the big mistakes a lot of students will look at this and say, oh, that 1 minus sine, I can do that's equal to cosine squared, right? Or cosine. Remember, those Pythagorean identities only work when we have a sine squared or a cosine squared. All right? And as of right now, another mistake students will do is they'll try to group the sine with the cosine and say, oh, it's just 1 over 1 minus tangent. Remember, cosine, this whole thing is divided by 1 minus sine. So we can't break it up across addition and subtraction. We can only break up our denominator across multiplication. So when I'm looking at this, what I'm going to want to do is think about, well, I need to be able to get this, Emily, into somehow I need to be able to transform the 1 minus sine squared. And to do that, I want, if I can convert this, if this was 1 minus sine squared, I could do something with this, right? But it's 1 minus sine. So what would I have to do to get this to be 1 minus sine squared? Yes?
Use conjugate.
I can multiply by the conjugate. Because remember, the conjugate is going to be like your difference of two squares, right? So if I multiply by the conjugate, 1 plus the sine of x, if I multiply that on the top and the bottom, then on the top, I'm going to have cosine squared times 1 plus sine of x divided by 1 minus sine squared of x. Right? Because remember, when you multiply a number by its conjugate, this is the difference of two squares. 1 times 1 is 1. Negative sine times positive sine is going to be negative sine squared. And your middle terms are just going to cancel out. The middle and the outer terms just cancel out. So now I'm left with 1 minus sine squared. Well, how can I rewrite 1 minus sine squared? Remember, sine squared of x plus cosine squared of x equals 1. So if I subtract sine squared of x on both sides, I have cosine squared of x equals 1 minus sine squared of x. So now I can rewrite this as cosine squared of x. So if I rewrite that as cosine squared of x, now my cosine squareds divide out. And my last expression I have is just 1 plus sine of x. Just remember, when you multiply by your conjugate, you have to do it on the top and the bottom. Yes?
Would the x still stay on the
No, that's cosine of x up there. Sorry. Got lazy. OK? So for this one, I'm just going to do a little bit of background to kind of help you out with this. First of all, let's go back with adding fractions. So if I wanted to add fractions, the main important thing I need to do is I need to make sure I have the common denominator. So what we look at this is my two denominators are 2 and 3. Therefore, to get the common denominator, what I need to do is find, what is the common multiple between 2 and 3? Well, to find the common multiple between 2 and 3, one easy way is, I can multiply by 3 over 3. Well, I notice the common multiple is 6. So therefore, to get both my denominators to 6, I need to multiply here by 3 and here by 2. To keep them equivalent fractions, I need to multiply the numerator and the denominator by the same term. Therefore, I have 3 over 6 plus 2 over 6, which equals 5 over 6. So that's how to add fractions when you have unlike denominators. The next thing we need to remember is, how do we simplify when we have a binomial by looking at our conjugate? And let's go and let's go back to radicals. Let's look at that. So if I had a radical, let's say I had 1 minus the square root of 3. And if you want to remember, when we try to get our radical off the bottom, what we always want to do is make sure we multiply by our conjugate. And the reason why we had to multiply by the conjugate is because when you take a number or a binomial and you multiply by its conjugate, what happens is you eliminate your square root. OK? So we eliminate by my square root, and therefore what we're going to do is get the conjugate. Now, one thing you notice about this problem is we have our two denominators. Now, you notice here the denominator, all I did was multiply by my other denominator. And that's just kind of an easy, simple way. It's not always the most simplistic, but in most cases, you're always going to be guaranteed to have, they're both going to be multiples of your new denominator. So that's exactly what I'm going to do for this problem. To get them to be like denominators, what I'm going to do is I'm going to multiply by the conjugate. So if I multiply secant squared of x plus 1, if I multiply by this other denominator, I am bound and determined to now have a multiple for both of them. So I'm going to multiply by the secant of x minus 1 on the top and the bottom. And then over here, I'm going to multiply by the other denominator, which would be secant of x plus 1. OK, now the whole reason why I kind of showed you the purpose of multiplying by its conjugate, because you notice that these are conjugates of each other for both denominator. And what's so important about that is before, we got rid of the square root. Well, we're not trying to get rid of our square root. But what we notice is multiplying a binomial by its conjugate is the difference of two squares, meaning that I can simply rewrite these. Well, first of all, as we multiply our numerators, those are just going to be the same. So I'll have secant of x minus 1 all over. Now, by multiplying a number by its conjugate, what I'm going to have is secant squared of x minus 1 squared. Or I'm sorry, minus negative 1 times 1, which is negative 1. And then over here, I'm going to have minus, secant of x plus 1 over, again, the conjugate, which is going to be the exact same thing, secant squared of x minus 1. Now, since they have the same denominator, I can combine them. So therefore, I have secant of x minus 1 minus a secant of x plus 1 all over secant squared of x minus 1. Now, let's see, can we simplify my secant squared of x minus 1? So we go back to my Pythagorean identities, which states my Pythagorean identities, yes, 1 plus tangent squared of x equals secant squared of x. Therefore, I can now rewrite, if I was going to subtract 1 on both sides, I can say that the tangent squared of x is equal to the secant squared of x minus 1. Therefore, I can now replace my denominator as as tangent. The next thing I can do is I can distribute my negative sign. So therefore, now I'm going to have a negative secant of x minus a minus 1. So therefore, now my secants are going to subtract out to 0. And I have negative 1 minus 1, which would be a negative 2 over tangent squared of x. So therefore, now you could look at this as rewriting it a couple different ways. We could so you could simplify this another way. We could also write this as tangent. So we could represent this as a negative 2 times cotangent squared of x. Or we could just leave it as a fraction of negative 2 times tangent squared of x. So there you go, ladies and gentlemen. That's how you simplify, that's how you subtract two trigonometric expressions. Thanks. One thing that we have is, if we want to go ahead and combine like terms, you guys can look at this. And the main important thing when you guys are trying to add, we have to make sure we have common denominators. All right. Now, for this one, I wouldn't really want to be looking into adding these. However, there are going to be some problems where you're going to have to add and subtract, meaning you're going to have to get common denominators. In this case, though, rather than doing that, I'm going to look at this and I'm thinking, all right, what are all these algebraic techniques? We worked on adding, subtracting, multiply, dividing. But a lot of times, we're also going to have to look into rhymes with tractoring. Factoring, right? That factoring stuff is never going to go away. Yes? This is cosine squared of x times cotangent squared of x. So now, to do this, what I'm going to have to do is factor out my common term. So when factoring out my common term, you guys can see that they both share a cosine squared of x. Therefore, it's going to be 1 plus cotangent squared of x. So by factoring out a cosine, I'm now leaving me with 1 plus cotangent squared of x, which, just like kind of the last problem, we know that 1 plus cotangent squared of x is cosecant squared. So I have cosine squared of x times cosecant squared of x. Now, again, that might not make too much sense to you unless we can rewrite the cosecant, which we can rewrite as 1 over sine squared. Then, as I multiply those across, I'm now left with cosine squared of x over sine squared of x, which equals tangent squared of x. Should be your simplified version. OK? So I'm looking at cosecant of x plus 1. And to get that off the denominator, what I'm going to want to do is multiply by the conjugate. Now, The reason why I'm going to want to multiply by the conjugate, because when you multiply a binomial by it times its conjugate, you produce the difference of two squares. And let me go and explain again. If I have a plus b times its conjugate, which would be a minus b, so you have the same terms, one positive, one negative, what you produce is the difference of two squares. And that's very important because we can do this multiplication without doing FOIL and writing it all out or creating a box and so forth like this. And it's important when producing the difference of two squares is because by not only is it easy to factor, but then also it provides us in trigonometry something that we might need to be able to write using our trigonometric identities. So by multiplying by the conjugate, I have cosecant of x minus 1. I need to make sure that I multiply my conjugate on the denominator and on the numerator to produce equivalent fractions. Now I'm going to keep my denominator the same. I'm not going to multiply that through. And the reason why you sometimes don't always want to multiply that through, you could easily multiply through and you get the exact same answers. But sometimes as far as simplified version, we're going to be factoring out terms anyway. So you might want to keep them in there before and see if you can maybe cancel things out, and then see if by distributing it, you would actually simplify terms. So therefore, now that's my numerator. And now my denominator is just going to be cosecant squared of x minus 1. So now it's important when using trigonometry, I see my difference of two squares is cosecant squared of x minus 1, which looks very similar to a Pythagorean identity, which says 1 plus cotangent squared of x equals cosecant of x. Now this is really important. There's the bell. Bye, kids. So if I want to solve for cosecant squared of x minus 1, I'll just subtract the 1 on both sides, and I get cotangent squared of x equals cosecant squared of x minus 1. So therefore, I can rewrite cotangent squared as my denominator. Now, why do you want to do that? Because you're supposed to get rid of your denominators, right? Very good question, Mr. McLogan. That's cotangent squared of x, right? OK. So now I have cotangent squared of x. And now what we're looking at is we have a trig identity. So what happens, think about it this way. If I have 1/4, right, and I need to get 1/4 off the bottom, what do we do? Well, or let's even do something more confusing. Well, let's go back to 1/4. I asked the question, so I might as well finish it, right? To get 1/4 off the bottom, we can multiply by the reciprocal, right? And just multiply by there, and you're still going to have, if you multiply by 1/4, 4/1, you're still going to have your 1/4, but you're not actually going to be getting it off. But let's take a look at 1/2 divided by 1/4. Well, here you're going to multiply by a reciprocal, which would be 4/1. And what happens is that's now going to get rid of now your denominator. So I look at a problem over here, and I say, what's the reciprocal of cotangent squared? Well, the reciprocal of cotangent squared is going to be 1 over cotangent squared, which is equal to tangent squared of x. So I'm going to multiply by tangent squared of x on your numerator and on your denominator. So therefore, what I notice is now, see, it's helpful that I didn't distribute this, because now I can just multiply tangent squared times tangent squared, which will leave me tangent to the 4th of x. Any number multiplied by its reciprocal is going to equal 1. And then I can just multiply that by cosecant of x minus 1. So there you go, ladies and gentlemen. That's how you simplify or rewrite a problem without a fractional denominator. Thanks. So, ladies and gentlemen, if you remember last class period when we were talking about factoring, we kind of went back through and did like a review of factoring techniques, right? And the first thing I went through is I said, let's practice just factoring in general. Let's do x squared plus 2x plus 1. And I said, just factor that, right? It was a pretty basic problem. I said, just factor it. And you said, what two numbers multiply to give you 1, but then add to give you 2? And majority, it was probably the first one that students were able to mark up, right? Students would say, oh, it's x plus 1 times x plus 1, right? Very good job. And then what I did is I kind of threw a little bit harder problem in there, and I said, well, what would happen then if I put it to the 4th power? And you guys weren't really confused. You're like, oh, well, that's just going to change the factors, right? It's still going to factor correctly, but now the factors are going to be x squared plus 1 times x squared plus 1, right? Do you guys see how to the 4th and 2nd power doesn't really change the factor, and it just kind of changes the factors, all right? So what we're looking at now is we just have a problem with tangents. So rather than just having the x's, all we're doing, ladies and gentlemen, is just putting in tangents in there. The factoring remains the same, But now your factors are going to include tangents. So therefore, the factored form of this is going to be what two numbers multiply, or not, what are my factors going to multiply to give me this trinomial? So it'd be tangent squared of x plus 1 times tangent squared of x plus 1. Which is really tangent squared of x plus 1 squared, right? Which I could have done that for all of those before, but I left it kind of separated out. So now what we need to look at is what is tangent squared plus 1 equal to? Secant squared. So you could really say it's secant squared of x squared, which is equal to secant to the 4th of x. Okay? So for this problem, we want to simplify it. And when looking at, we look at our Pythagorean identities. We know that sine squared plus cosine squared equals 1. But the main important thing, guys, when trying to simplify is, we're going to want to get rid of this denominator, right? And once I know that I have sine squared and cosine squared, I look at this and I say, well, let's try to get them to be the same term. Because our main important thing when we have a denominator, especially with multiple terms, is we want to try to get this to a monomial denominator. We want to try to combine our terms somehow that we're going to have a monomial denominator. So like I said, I have sine squared of x plus cosine squared of x equals 1. Well, if I solve for sine squared of x, I get sine squared of x equals 1 minus cosine squared of x. All right? So if we can at least make them all signs on the bottom, then, Elizabeth, we can at least combine them and see what we get. So I'll have 2 sine of x cosine of x divided by sine squared of x plus sine squared of x. Now, hey, that's cool, because now I have a binomial, but I can combine them, right? So now I have 2 sine of x cosine of x divided by sine squared of x. Now, the next thing you guys need to remember is sine squared of x is equal to sine of x times sine of x. Yeah, it is a 2. Sorry, thank you. So we have sine squared of x is equal to sine of x times sine of x, right? So in reality, we have 2 sine of x times cosine of x divided by 2 times sine of x times sine of x. And the reason why I just write it out there is you can see that 1 sine of x divides out to equal 1. The 2's divide out to equal 1, just leaving you now with a cosine divided by sine, which is cotangent of x. Cool? All right.
Can we find a common denominator? We found common denominators with x plus 1 and x minus 1. Can we find common denominators here? Well, look at the denominators. What do they have in common? It's just the product of them. The least common denominator here would be cosecant squared of x times secant squared of x. So all you'd have to do to get common denominators would just be multiplied by cosecant squared of x times cosecant squared of x, secant squared of x times secant squared of x. And then you could do that, and you can multiply them, you can get common denominators. However, I did that, so I'm going to save you some trouble. I did that, and you could continue working on it. It's not a problem. I'm sure you're going to get to the same answer I am. But what I realized was, you know what, before I actually combine fractions, one thing that we learn in algebra is before we start doing a lot of stuff is to always look to simplify something first, right? Yes? So what I decided to do on this problem was, you know what if maybe something might simplify out here first. Before I combine fractions, let me simplify this, or let me see what they are. So what I did is I decided to write everything in terms of sines and cosines. And you might say it doesn't look any cleaner, but I just want to kind of see what everything looks like when I do this. Okay? Now what I'm going to do is I'm going to simplify this. I'm going to get these fractions off the denominator by multiplying by the reciprocal. That's important because all those go down. Now, a couple things happen here. What's cool about what actually Bound, that was bound. So when I multiply this out, I now get sine cubed over cosine of x plus, here, my cosines divide out. I'm getting sine of x times cosine of x. And you could always put that over 1. I think it's always helpful to put things over 1 so you just don't forget they are fractions. All right.
Wait,
Yes?
can you go straight to like multiply by the reciprocal?
From up here? Yeah, I just didn't do it that way. So if you did it that way, if you want to see where your answer is, that's perfectly fine. I decided to do it a different way. I don't know if it's better. It could be faster. It could be slower. I don't know. I just figured it was worth a shot. Yes? Can you wait till I'm done? Because I thought you'd want to be writing this down until I was done, right? Oh, that's interesting. All right. So what's the common denominator of cosine in 1? I want you to do this one. It's just going to be cosine. So I'll multiply by cosine of x over cosine of x. And now I obtain sine cubed plus sine of x cosine squared of x all over cosine of x. Now, it might not seem too much to you guys and be like, well, this still doesn't look that better. But can I factor anything out in the numerator? Close. What do these two terms share? Sine. So if you factor out a sine of x, you get sine squared of x plus cosine squared of x all over cosine of x. Yes? Huh? It's always of x. Always. Or of theta, or of y. There is no such thing as y sine or cosine. It's always of an angle. Yes?
So you wouldn't make it sine of 4x, just be sine squared of x.
Talking about here? You mean why you can't combine those? Yeah, because this is attached to that. So that's like saying 4 plus 4x is 5, or 5x, right? That does. So since that's multiplied by cosine, you can't combine them. Guys, what's sine squared plus cosine squared? 1. It's in your identities. And then what's sine divided by cosine? Tangent. So the final answer is tangent.
I think I almost got all of that.
OK, so for this problem, to verify, we're obviously going to go and look at our left side. And we're just going to want to apply our operations. So when we look at our paper, what we have is we want to see. OK, so the main important thing, ladies and gentlemen, is we want to look into multiply. Now, unfortunately, like the last problem we did, that was a difference of 2 squares. So it's pretty easy to multiply that through. However, this is not a difference of 2 squares. It is a difference, but these are not the same square numbers. So therefore, we're going to have to apply FOIL, or just our property of multiplying 2 binomials. So therefore, when we do that, we have tangent squared of x times cosine squared of x minus tangent squared of x plus cosine squared of x minus 1 equals our right side. We're just going to leave it like that. Oh, you remember what I did. All right, so the next thing that we're going to do is I'm kind of converting. We have to add all these terms that do not seem like they're like terms, do they? All right? No. These are none of the like terms. So the next thing I'm going to do is I'm going to convert to sine and cosine and see what kind of common denominators that I might be able to get. So tangent squared is going to be sine squared over cosine squared of x times cosine squared of x minus sine squared of x over cosine squared of x plus cosine squared of x over 1 minus 1. Okay, so I just kind of converted everything to a fraction, and if it wasn't a fraction, then I put it on top of 1. Now, what we notice about this is, first of all, these cosines are going to divide into 1, just leaving us with a sine squared over 1. And then, if I wanted to add all these up, all I simply need to do is multiply by cosine. I think that's the problem that I did here. Actually, I don't remember what I did here.
So therefore, we have sine squared times cosine squared. Oh. That's minus. Did I? Cosine plus 1 minus 1. I did something wrong. Oh, no, I'm sorry. Yeah, you're right. Okay. Well, I don't know. Let's just rewrite it and let's go through it. My work's not very clear. I can't remember what I did. So let's just go through that and see what happens. Okay. So that means, ladies and gentlemen, what I need to do is get these all to have the same common denominator, right? And then I can add them. So I'll multiply by cosine squared over cosine squared of x. Here I'll multiply by cosine squared of x. Oh, no, that was it. I was right.
Oh my god.
Well, look it. We don't need to go through. You guys notice I have a sine squared and a cosine squared, right? So these sine squared plus cosine squared, what does that add up to? 1. I just rearranged it in my problem. So now I have 1 minus tangent squared of x plus 1. I'm sorry. So I have 1 minus tangent squared of x minus 1 equals my right side. Now, 1 minus 1, those now cancel to negative to 0, and I'm just left with tangent squared of x. You're right. You don't need to add them up. I had those sine and cosine squareds right there. I just couldn't see them as I wrote it in there. Do you guys see what I did?
Oh, yeah.
I'm confused about the sign of the one.
You don't need to. I was thinking, that's what I was thinking I would have to do, but I didn't have to because I already have sine squared and cosine squared. Sine squared plus cosine squared equals 1. So that equals 1 right there, minus, that's really tangent squared, so I can convert that back to tangent. And then my original problem said minus 1, so 1 minus tangent squared minus 1. The 1's now go to 0, so just leave me with negative tangent squared of x, which is on the right side. All right? So I converted to sine and cosine so I could actually only cancel it to divide that out to 1. And then I actually already had everything else I needed. So it's not a difference of 2 squares, so I actually have to multiply every single term. So 1 times 1 is 1. 1 times cosine is cosine of beta. 1 times negative sine of beta is negative sine of beta. Negative sine of beta times cosine of beta is negative 1. Does everybody agree with me that sine times cosecant is 1?
No.
OK, what's the problem?
It's number 5 that you wrote on the board. It's that, but you changed it.
Oh, it's cosecant up there? So this is cosecant. OK, thank you. Sorry about that. Oh, that would make sense, right? Cosine would be that. So what the heck did I do? So that's cosecant. Yeah, I was like doing it in my head. But that's still negative 1. I said it wrong, but I should have.
So sine, like cosine.
So cosecant and sine
Are reciprocals of each other. Anytime you multiply a number by its reciprocal, it's 1, right? Is everybody OK with that first step? No? No? Good? OK. What's up?
Wouldn't it be like sine of beta times cosecant of beta?
Yes. Sine of beta times cosecant of beta. Cosecant of beta is the reciprocal of sine of beta. So it's 1. That's why I wrote 1 there. And since that's a negative sign, it's negative 1. Does that make sense? OK. All right. So now, obviously, you guys see we have 1 minus 1 is 0. So that's not going to be included. And then the other thing is I have sine minus. Oh, that's already there. Oh, that was simple. Done. Verified. Same as the other side.
Huh?
That's it. I just wanted you to multiply and simplify. OK. If I was going to be looking at this problem, it says cosecant squared of theta divided by cotangent of theta equals cosecant of theta times secant of theta. Ladies and gentlemen, if I was going to do this one, if I'm going to look at my complicated side, I'm going to say this is obviously going to be my more complicated side, right? So dealing with the fraction, I have the cosecant squared of theta.
one thing we could look at would be transferring this to a trig identity, right? But the main important thing I also want to do is, this is a fraction and this isn't a fraction. So let's get rid of our fraction. Yes?
It's supposed to be CS.
Yeah, see.
What?
Because you got CCC.
Yeah, it's supposed to be, yes. It's not Canterbury workwear, it's cosecant, thank you. So what I would do is, first thing is I'm going to get rid of this fraction. So you guys remember, how do we get rid of our fraction, right? We always get rid of what's on the bottom. We get rid of what's on the bottom by multiplying by the reciprocal. So if cotangent is on the bottom, to get rid of it, I need to multiply by the reciprocal. The reciprocal of cotangent is tangent of theta. So I multiply tangent of theta on the top and the bottom. Those now cancel out because they're reciprocals of each other. So therefore I'm left with tangent of theta times cosecant squared of theta equals cosecant of theta secant of theta. Now, if I look at this cosecant, all right, if I go and look at my trig identities, cosecant is going to go and provide me a cotangent, right? So a lot of you might say, hey, let's go and transfer to a cotangent. Well, that might not always work in your best direction. You can go and try it and see where you come up with. But if I'm looking, remember, I'm trying to keep my left and my right side the same. If I throw in a cotangent there, on the right side, there's nothing with the cotangent. So before I try that, I'm going to say, how about I need to get rid of this cosecant squared, right? So I'm probably going to have to do some canceling out. So what I'll do is I'll convert this to sine and cosines to see if I can cancel anything out. Did everybody see what I did? Why did I do this rather than changing it to trig identity? Because remember, I have a squared, so I want to get rid of the squaring. Well, what I notice is my sines are up there can cancel out. So if I was going to multiply these cancel out, I could be left with 1 over cosine theta times 1 over sine of theta. Well, 1 over cosine of theta is going to equal secant theta. 1 over sine of theta equals cosecant of theta, which equals the right side. Yes?
How did you get one one cosine?
What I did is I just canceled these out. If you were to you could like multiply them out if you wanted to. What I did was, you just notice that, you know, it's sine divided by sine. These are all multiplied, right? These are multiplied, so those two can cancel out.
But don't you cancel out the 1 and you cancel out the sine?
The what?
Well, I thought it would be just or cosine.
No, because remember, they cancel out, there's still going to be a 1 there. The cosine is still on your denominator, right? The cosine is still on your denominator. You can't just move it up to a numerator. It's still going to be on the denominator. That's why it's 1 over cosine. Does that make sense? Think about it this way. If I did, I'll end the video and I'll show you with some numbers. So when looking at a problem like this, what we want to do is we're going to have to verify the identity. And the first thing we want to do is, when looking at verifying identity, is we just want to pick one side, all right? Because what we're trying to do is we're trying to prove that one side is going to be equal to the other side. So what you're going to want to do is just isolate. The best kind of practice is just to isolate one side and just focus on that first side. Now remember, when focusing on the side, what I want you to do is simplify that one side so you can hopefully show that it looks like, or that it's equal to the other side. So therefore, when trying to pick the side, the best practice is usually to pick the side that's going to be the most complicated. So by looking at these two sides, you can say, all right, well, obviously, this is a lot more complicated than this side. So let's work on, see if we can simplify this left side so then it would be equal to sine squared. So the first thing you're going to want to look at is, yes, you know you have a fraction, all right? And there's one way you could do it by splitting it up. This way, first way I'm going to show is, let's transform our trigonometric identity and see what's going to happen. So when we rewrite this as a trigonometric identity, if I have sine squared, right, because we know we want to get this as sine. So if I take a look at secant squared, we know that secant squared is going to be 1 plus tangent squared. So I could rewrite this as tangent squared plus 1 minus 1 divided by secant squared of theta equals sine squared of theta. Now, you might say, well, why didn't you convert the other sine squared, right? Well, if I converted the other sine squared, then I would just have two tangents again. And 2 tangents is not going to help me get to sine, right? So I'm only going to convert the top just to kind of see what happens. I'm just playing around here. Well, what happens, this is nice because now I know that my +1 and -1, those cancel out to 0. Therefore, I'm now left with tangent squared divided by secant squared, these are all of theta, is equal to sine squared of theta. All right? Then what you can look at this is saying, all right, well, we need to get secant off the bottom, so we can multiply by the reciprocal of secant, which is cosine. So if I multiply by cosine squared, now that's going to multiply to 1. Cosine squared over this is going to leave me with cosine squared of theta times tangent squared of theta equals sine squared of theta. And remember, tangent is what? Sine squared over cosine squared. So if I converted the tangent to sine squared of theta over cosine squared of theta, you notice that my cosines divide into 1. Therefore, I'm finally left with sine squared of theta equals sine squared of theta. Which question? All right. Did you follow me from here? I multiplied by cosine over cosine. Right? And then I multiplied cosine times tangent equals sine. Well, I converted tangent by using the quotient identity. Tangent is converted to sine over cosine. So therefore, the cosines divide to 1, so I'm just left with sine equals sine. I guess I probably could have wrote in equals sine of theta, sine squared of theta. Okay, and therefore you can say it's now been verified. Cool? Very good. All we're simply going to do is, we're going to apply our operations to verify our identity. So the main important thing is we want to pick one side. I'm going to pick the left side because I know that I have to combine these if I'm going to ever make it look like the right side. If I pick the right side, that means I have to separate it either by using addition or subtraction, which might get a little difficult. So I'm going to choose the left side. And what I'm going to do is, and obviously, if here they're separated by an addition sign, and these are multiplied. So therefore, I need to combine these two terms. Well, you can't combine tangent and cotangent. They're not like terms. And even by writing this as 1 over tangent plus 1 over cotangent, that's not going to help you out either because, again, those don't have common denominators. So there's a couple different ways you guys can do this. All right. Some students just converted 1, which I liked, and they left it in terms of tangent. And that's a good method because now, to get common denominators, you just have to multiply by tan over tan, right? Therefore, you're left with 1 plus tangent squared of alpha over tangent of alpha. Because when you multiply this, you get tangent squared. So plus 1 over your common denominator of tangent. Then you can convert 1 plus tangent squared into secant squared. Over tangent of alpha. Then what we can simply do is just multiply to get the tangent off the bottom. You can multiply by cotangent of alpha on the top and bottom, and you're left with secant squared of alpha times cotangent of alpha. Now, this might make a little sense. You might say, well, what exactly, what do I have here? Well, remember, secant is going to be 1 over cosine squared of alpha times cotangent is going to be cosine of alpha over sine of alpha. Therefore, those can divide out to 1, which is just going to leave you with secant of alpha over cosecant of alpha, which is your exact same answer. Okay? The other way you guys could do this, and this is all by doing it on the left side. The other way you guys could work this is also just convert everything to sines and cosines, right? Just convert, remember when I said that's the last step, to convert everything to sines and cosines and see what it looks like. So if you get stuck and you don't know what to do, I didn't see a lot of people get stuck and just write cosines and sines. if you get stuck, convert everything to sines and cosines. So cosine, sine to cosine. So if I was going to still do the left side here, I could do, I would have cosine of theta over sine of theta plus sine of theta over cosine of theta. Well, or alpha, right? Yeah, thanks. So to combine like terms, I need to multiply here by sine of alpha, here by cosine of alpha over cosine of alpha, leaving me with cosine of alpha squared plus sine of alpha squared all over cosine of alpha, sine of alpha. Well, on the top, that goes to 1 over cosine of alpha, sine of alpha, which is secant of alpha times cosecant of alpha. Okay? So there's two different methods, ladies and gentlemen, for you guys to be able to solve this problem. Okay? I know it wasn't easy and stuff, but make sure you guys write down that you have that answer so you guys can kind of remember the process to work on. Okay? All right. So, ladies and gentlemen, what we're going to do is we're going to kind of follow our guidelines to verify trigonometric equations. So all we're trying to do is just say that one side of an equation is equal to the other side of the equation. All right? And so I told you guys to write down these steps so you guys can just kind of follow along. Now, we don't always have to get through all 3 steps. A lot of times, just 1 or 2 steps is all we need. All right? So the first thing is we just want to kind of pick a side to work on. And the side doesn't really matter, but usually we like to pick the side that's going to be the most complicated. And whatever you can work on to simplify it. So what we're going to do is you're going to pick a side and then simplify that side. So hopefully it's going to look like the other side. And then you can verify that that you have a true statement or an equation. So what you want to do, a lot of times, we say pick the most complicated side. And just in reality, if you guys go back to step 5, just try something. If you don't really know, there's no right or wrong answer. Pick a side and then see what you can do on it. All right? So by looking on this one, I'm going to choose the left side because I know these are not like terms. You could work on something on the right side, but I'm going to maybe try something on the left side. And actually, you know what? I'll show you on the left side, and then we'll do something on the right side. So let's work on the left side first. I want to get this off of the denominator, right? I need to get rid of the cosecant. So to get rid of the cosecant, I can multiply by the sine of t on the top and the bottom. By multiplying by the sine of t in the bottom, now I don't have a fraction. And that's good. The reason why I did that, because does this have any fractions over here right now? No. So now I've eliminated the fractions. Then I need to see, what does cotangent equal? Well, cotangent equals cosecant squared minus 1 using Pythagorean identities. Yes? OK. So you have sine of t times cosecant squared of t minus 1 equals cosecant t minus sine of t. All right, now you can apply Pythagorean identity or distributive property. What'd you say?
I can't see.
I know, that's why I asked you to move to a different spot, right? So therefore, now you have sine of t times cosecant squared of t minus sine of t. Now I'm just going to continue working on the left side. So I'm just going to, we know that the right side already equals. Therefore, sine of t times cosecant of t. And remember, cosecant is 1 over sine, right? So therefore, I'm just going to be left with cosecant of t minus sine of t. Which, does that equal what's on the right side? Yes. Does everybody see how I got to there? Want me to go over that? OK. So remember, ladies and gentlemen, sine of t times cosecant. Cosecant is equal to 1 over sine. Right? So therefore, when I'm multiplying this, I have sine of t times cosecant of t. So therefore, that's 1 over sine of t squared. So therefore, 1, you're just going to be left with 1 over sine, which is cosecant of t. Does that make sense? Yes?
Where'd you get cosecant squared? Oh.
Pythagorean identity. I use my Pythagorean identity if we go there to there. Does anybody have any other questions on that, on this problem? But you guys can see now we verified that the left side is equal to the right side. OK? Good. So ladies and gentlemen, what I have, secant of y plus tangent of y equals cosine of y divided by 1 minus sine of y. So we need to go ahead and divide. We need to determine what side we'd like to work on. Remember, you always want to usually want to work on the side that's going to be the most difficult. Once you've picked the side that's going to be the most difficult, the next step that you want to do is kind of look into adding terms, getting the same denominator. You want to get variables off your denominator. So there's a lot of different routes you could go. You could say, well, I would like to work on this side, and then I want to add my terms. Or you could say, I want to get on this side, and I want to get my 1 minus sine of theta off the denominator. And what I'm going to look into, since these are two added terms, and this one's in a fraction, you got to look at, I'm going to probably state, since I can't combine these, and I've showed you how to combine these two, I'm going to work on the right side and get this off as a fraction. So I'm going to get the 1 minus sine out of the denominator. So by doing that, because what you notice is if I split that up, actually you can't split it up, work through. So to get this off the denominator, what I'll have to do is multiply by 1 plus sine of theta, or sine of y. Okay? So if you multiply by 1 plus sine of y, therefore you'll be left with cosine of y plus cosine of y sine of y divided by, on your denominator, you now have, actually, you know what am I doing? I'll leave that there. Therefore, then on the bottom, you're going to have 1 squared minus sine squared of y. Yeah, that's what I should have done. I'll just leave that out there. I'm not going to multiply through on your top. Sorry. So you're left with 1 squared minus sine squared of y. When doing that, you could say that, well, this now by using Pythagorean identity is going to give me with cosine squared. So I have cosine of y times 1 plus sine of y. And you can see what I started seeing in this problem was that I was probably going to, as Yusef wants to say, cancel out. But in reality, what I'm really doing is a cosine divided by cosine is going to divide to 1. So since I have two cosines multiplied by each other, that's just now just going to be a cosine of y. And that will now be eliminated into 1. So therefore, now I have 1 plus sine y divided by cosine of y, which can be separated into 1 divided by cosine of y plus sine of y divided by cosine of y, which we now know equals secant of y plus tangent of y, which you guys can see is right on your left-hand side. What step did you get confused on?
Like what, how'd you get sine?
What I did is I divided my cosine into 1 and cosine into sine,
Oh.
because that divides into both terms. Okay. We need to decide, should we be working on the left side or should we be working on the right side? Now the next thing I also know is I want to, whatever side I pick, I know that, so when I'm looking at a problem like this, and again, I'm trying to give you guys my rationale of thinking. First thing I know is I know that cosine and secant are reciprocals of each other, correct? Right? So I don't really want to get too far. I want to try to keep them within the same family can. And as long as I can keep them working through there, that's I just need to basically pick a side and go through. But I don't want to get crazy trying to get them away from their two functions. I'm going to decide to work on the left side. And it doesn't really matter which side you pick, but you just got to pick a side. Now, the one thing I understand, at least the one thing that I know is if I multiply by 1 plus cosine squared, what that will do is that will give me or if I multiply by 1 plus cosine of x, what that will do is that will give me a new trigonometric identity. So 1 plus cosine of x over 1 plus cosine of x.
So the top, go ahead, the top gives you a perfect square trinomial, whereas the bottom is going to give you a secant squared of secant of x plus 1, secant of x minus 1. So that's secant of x minus 1. I wrote these wrong. Correct? Okay. All right, so let's go and try this. So therefore, this is going to multiply out, and this is going to give me 1 squared plus 2 cosine of x plus cosine squared of x all over 1 minus cosine squared of x. And when looking at this, I can realize that, well, by doing this method, I mean, that looks pretty good, but the only problem I'm seeing with this is, I mean, 1 minus cosine squared of x is going to equal to what? Sine squared. And I could rewrite this as, sine squared minus 1, right? Or cosine of x equals 1 minus sine squared, correct? So if I look at that again, if I rewrite those, but why do I really want to go into sine? Because all I need to do is make it look like secants, right? So if I rewrite this as sine squared of x minus 1, so if I replace cosine squared of x with sine squared of x minus 1, and then I rewrite this as the sine squared of x, well, the 1's cancel out, but I'm not really getting anywhere, am I? It's 1 minus. Yeah, it'd be 1 minus sine squared. You're right. But you guys see, by doing this, this is really not helping me out. Now, if my other side was equal to like something in sines or cosecants, then this would make sense, right? But my other side is not in terms of sines or cosecants, right? So converting from cosine to sine is not really doing me any justice. It's not helping me out. So guess what? My initial thoughts and intuition is probably not going to, it's not like I did anything wrong, but it's probably not going to help me out. And yes, it's OK to keep writing this down, because guess what? That's the process of solving these, is just to try and erase. All right, so let's think about another thing. One of the things Mr. McLogan said is, think about all our operations. Is there anything else? I mean, I could obviously multiply by secant of x plus 1, but then that's going to do the same thing, because secant of x goes to tangent, right, using your Pythagorean identities. And I want to get it to look at the cosine. So the last thing, the last step, if stuck, write in terms of sines and cosines. So let's try that. Why don't I rewrite this in terms of cosine? So I'd write 1 over cosine of x plus 1 all over 1 over cosine of x minus 1. Oh, you know what I could do here? I know what I need to do. Never mind. This is even easier than that. Watch this. It finally just dawned on me. This is so much easier. I remember a problem like this. So this one's even easier. If you guys look at this, by doing that, I just realized I'm not going to get anywhere anyways. It's not going to help me out because, well, let me show you. If I did 1 sine cosine of x plus 1 all over 1 over cosine of x minus 1, what can I do here? I can what? Combine them, right? I mean, if I combine them, then I'm going to have single monomials, right? I'm going to have a function over function. That's not going to make it look like this, correct? So I'm spending this like 5-minute video here for an answer that's much easier. But I want you guys to think through my thinking. And this is OK. You tried all these things, right? You're like, I can't figure it out. Well, think about this, guys. Again, remember, as long as you multiply the same number or function in the numerator and the denominator, you're not changing something, right? If I have 1/2 and I multiply that by 4 over 4, that gives me 4 over 8. That is equivalent to 1/2, correct? So watch what happens. What would happen then if I just multiplied this by cosine of x on the top and the bottom? What would happen when I did that? Well, now I would have cosine of x times the secant of x plus 1 times the cosine of x all over secant of x times cosine of x minus 1 times cosine of x. What?
I'm guessing it's either cosine xx,
Cosine.
top one.
He wrote secant of x without
So, by doing this, what's cosine of x times secant? What's cosine times secant? 1. 1 plus cosine of x all over 1 minus cosine of x. Guys see how it's exactly the same?
Yeah.
Verified.
Can I take a picture? Wait.
All right, so on our final problem here, we have cosine of x minus cosine of x divided by 1 minus tangent of x equals sine of x cosine of x divided by sine of x minus cosine of x. So we want to verify this identity. And this looks pretty crazy looking at saying, hey, this left side is equal to the right side. And so what we need to do is we need to find a way to somehow verify that, yes, indeed, these two sides are equal to one another. So again, by following our guidelines, we just want to stay on one side. Let's just pick one side to start off with and just work on one side to simplify it. All right? Now, we usually like to say, find the most complicated side. And like I said, that can be a very arbitrary decision on your part on which one is going to be the more complicated. When looking at this, I see that this is written out in 2 terms, and this is written as 1 term. I usually like to combine my 2 terms, so therefore it's written out as 1 term, and then see what I can do after that. So in my recommendation, I'm going to work on the left side. And let's just see how far we get with working on the left side and see if we need to do anything further. So if I was going to work on the left side, I could rewrite this as over 1. And therefore, that would tell me that I would need to add them, right? The next thing is to apply my operations. So it's asking me to subtract these 2 terms. So let's go and subtract, right? So what I'll do to subtract is I need to get the same denominator. So I'm going to multiply by 1 minus tangent of x on the bottom and the top. OK, so therefore, what I'll have then is 1 minus tangent of x cosine of x minus, actually, let's distribute that. So if I distributive property, I'll have cosine of x minus tangent of x cosine of x minus cosine of x, all divided by 1 minus tangent of x. And we, of course, want that to equal sine of x minus cosine of x, right? OK. Well, the important thing is we notice that cosine of x minus cosine of x just goes down to 0, right? So that's kind of nice. And then so now I have is a negative tangent of x cosine of x divided by 1 minus tangent of x. Now this is where it's going to get a little confusing. So we're almost there. We kind of have something pretty similar, right? We have 2 terms multiplied up top, and then we have 2 functions subtracted on the bottom. Over here, we have 2 terms multiplied up top, and we have 2 terms that are being subtracted on the bottom. The only problem is they're not the same, right? They're not the same terms being subtracted or even multiplied. So what I want to do is maybe see, well, what could I maybe do to get them to be the same terms? On the bottom, I need to subtract sine of x minus cosine of x. All right? Right now, I have 1 minus tangent of x. And up top, I have tangent times cosine. I want to see, well, maybe what could I do to multiply that back out? So one thing I noticed is let's convert things to sines and cosines and see what's going to happen. All right? Because I'm kind of stuck right now. I don't know of any fundamental identity I can use. So let's go ahead and
let's go and use our convert everything to sines and cosines and see what's going to happen. So I'll convert to sines and cosines. Therefore, I get negative sine of x over cosine of x times cosine of x divided by 1 minus sine of x over cosine of x. Well, when writing it like this, we notice that my cosine of x are now going to divide out to 1, right? So now I don't even have a cosine up top. And therefore, what I also notice is I now need to multiply. If I need to get this multiplied by cosine. Well, since it's a fraction, if I take a cosine, and as long as I multiply it on the top and the bottom, cosine of x times cosine of x, my fraction is going to be the same. So what I'm going to decide to do is, how about I multiply the top and the bottom of my fraction by cosine of x? You can do that. It's like taking 2/4 and multiplying the top and bottom by 4. Right? Then you'd have 2/4 multiplied, so you have 8/16. Is that still equal ratio? Yeah. So let's multiply by cosine over cosine. So what happens now is I get a negative sine of x cosine of x divided by, when I apply this cosine to the top, I distributive property this, and I'm left with cosine of x minus, now these cosines are going to divide out to 1, minus sine of x. And you're saying, oh, good, you got it. Close. Because, yes, we have, well, first of all, this is a negative sine of x times cosine of x. And this is sine of x minus cosine of x, right? It's not the same. So what we can do is, how about let's factor out a -1 on the bottom. If I factor out a -1, so I pull out, I divide both terms by -1, what that's going to leave me now is a negative cosine plus sine of x. And therefore, my negatives on the top and the bottom, if I factor out the negative on the top, therefore my negatives are now going to cancel each other out, and therefore I'm left with, this equals a now positive sine of x cosine of x divided by sine of x minus cosine of x, which, of course, is equal to our right side.
So in this example, what we want to do is, obviously, you can see they look kind of similar to each other, don't they?
Yes.
Pretty similar. Like, what side is really more complicated than the other side? So in reality, guys, I would just say the best thing to do is probably just, my recommendation would probably be to just multiply here by, or pick a side and run with it and see about different things you can do. Might be might be right, it might be wrong. Let's just try something. So, one thing I might do is, I could multiply by the conjugate on the top and bottom over here. I could multiply by the, I could also multiply by the reciprocal on the left and right. Let's try that actually. So if I wanted to get rid of this, well, that's going to give me 1 here. So let's multiply by the conjugate. Let's see if I can get this down to one term. So if I multiply by the conjugate, I'm going to get 1 minus sine of beta, 1 minus sine of beta. So when doing that, I get cosine of beta minus sine of beta, cosine of beta, all over. Let's do 1 minus sine of beta times 1 plus sine of beta. I'm not going to multiply it out yet because I just want to kind of see what kind of occurs here. And I see what happens. I see what I'm going to want to do. Well, if I factor that out, the 1 minus sine of betas would multiply out, but I don't want that to happen yet. I want to leave that up there. So let's actually multiply this out. This is going to give us 1 minus sine squared of beta when you multiply a difference of 2 squares. which using your Pythagorean identities is equal to cosine squared. I can factor out a cosine in the numerator. Cosine of beta, 1 minus sine of beta, all over cosine squared of beta. Now, do you guys see that a cosine divides out? And I'm just left with 1 minus sine of beta over cosine of beta. And there you go. Now, I should actually kind of say here first, we could apply the operations, right? But you guys remember what I did in that homework problem? I did the operations, and I was like, wait, stop. Why don't I try simplifying this first, right? And I would recommend doing that first before you get deep into applying operations. See if there's something you can initially simplify. And in this case, I want to just kind of see if I could rewrite this. I'm definitely going to choose the left side. But if I rewrite this in terms of 1 over cosine and 1 over sine of x, plus sine of x over cosine of x, let's maybe try to simplify this to one trigonometric expression. So I'll multiply by the sine of x over 1. And what I get is the sine of x over cosine of x plus the sine of x over cosine of x. That wasn't that bad, right? That was much easier than trying to get common denominators and combining them, right? So I should actually kind of add something in here, is try to see if you can maybe simplify first. If you go right into getting common denominators, and that's fine, it just might be a little bit more work than we're going to do. So remember, we need to get to tangent of x, right? Well, what's sine over cosine? Tangent of x. Tangent of x plus tangent of x equals 2 tangent of x. Done. So this is an example, guys. We've got to pick a side, right? So the best side to pick would be the left side, right? I definitely picked the left side. Now, you got to think. We have adding. We have adding and division on the left side, and we just have multiplication on the right side. So we have to combine those operations so we can get them to be. So we know we're going to be adding some fractions here eventually, right? One thing that I would do is I think I need to, instead of multiplying by the conjugate here, I think my best thing is let's look at what we have, and let's instead of combining terms, I am going to try to get rid of all these fractions. So first thing I'm going to do is rewrite this in terms of sines and cosines. OK, so like my fraction over there, what I would do is instead of combining these, I would look into multiplying by the, bless you, I would look into finding the common denominator. So what is my common denominator between cosine, sine, and 1? Least common denominator would be the product of sine of x, cosine of x. So what I'm going to do is I'm going to multiply everything by sine of x, cosine of x. By doing that, I now obtain sine of x plus sine squared of x all over cosine squared plus sine squared cosine squared. I'm sorry, cosine of x. That's just cosine of x. No, that's cosine squared of x plus Everybody follow me?
You forgot the cosine squared of x.
All right. I don't know. I'm not sure if that's really helping us out to do. I'm not really sure if that's a better way of doing anything.
Where did you get the sine squared?
Oh, it's just a sine, right? Okay.
Wait. Oh, but then you factor out the
Yeah, I mean, I could factor out a sine. I don't know. Let's go and factor it out and see what we have.
You can factor out sine and then factor out cosine.
Okay, actually, this is not too bad. So I was kind of confused. Diana, as far as I didn't really know if I was doing it right or if I was on the right path. So all I did, Griffin, was I just stopped and I said, well, exactly what Josh said. It's like, well, we could factor something out. I don't know if that's right or wrong, but we can do it. So why don't we do that? And that's the whole thing, Lauren, is about these problems, is again, just try things. I know I can multiply by the common denominator. That's what I'm going to do. So, but now by factoring these out, those divide out. And then cosine squared is really sine of x over cosine of x times cosine of x. Well, what's sine of x over cosine of x? Tangent. What is 1 over cosine? Secant of x. Done.
All right, ladies and gentlemen, what we're going to do is we're going to do some solving. And the best thing I can help you guys out with this solving is forget about the trig signs. Okay? When you're first going to be working these, if you're having trouble with them, just treat it like you're going back to Algebra 1 and forget about the trig signs, or the trig functions. So to solve this, you guys should know, first thing we always do is undo addition and subtraction, right? Then we always undo division and multiplication. Okay? Everybody understands that, right? That's good. Well, for here, it's the exact same thing, except now it's rather than just like a cosine of x, now it's rather than just x, it's cosine of x. So I'll add 1, divide by 2, and now I get cosine of x equals 1/2. And remember, we got to think about this. What does that solution mean? Well, first of all, what does our x represent? Remember our x, we take the function of an angle, right? It's the cosine of your angle equals 1/2. So then I need to go back and think, oh crap, I need to figure out what angle does cosine equal 1/2. And then we need to remember, well, what does cosine represent? Remember, cosine represents our x value when we're talking about a coordinate point on the unit circle. So we look at that and we say cosine, when does cosine equal 1/2? And yes, pi over 3 is one answer. Is that the only answer?
No.
What's the other answer?
-2 or -1 over 2 and -3.
Well, be careful. If you
1 over 2
it can't 1 over
Negative pi.
Yeah,
One of the negative.
Negative pi.
okay, yes, you could have your you could have your negative pi over 3, but if I was going to look into a positive angle, it would also be
5.
5 pi over 3. Yeah, that was just the answer I was looking for. This one also equals positive 1/2 negative radical 3 over 2. But since we're only dealing with the cosine, we can see that my two angles are 5 pi over 3 and x pi over 3. So therefore, I'm going to have two answers, right? I can say that x equals pi over 3 and x equals 5 pi over 3. Does that make sense?
Yeah.
Right? But now, ladies and gentlemen, remember what I talked about with our graph. Our graph keeps on going on and on and on forever, right? So in reality, these are my only 2 points. I also have to make sure I add 2 pi. Well, how many 2 pi's do you add? Do you add just 1 2 pi, 2 2 pi's,
Infinite.
3?
Infinite.
You're gonna, yeah, well, you need to be able to add as many 2 pi's as possible, right? Because this graph goes on and on and on and on and on forever. So if you're saying when it equals, 1/2, it needs to cross at 2 pi here, 2 pi here, 2 pi there, 2 pi there. So we need some way to represent adding an infinite number of 2 pi's. And what we use is just the integer n. Okay? Because if n was 0, my answer would be pi over 3. If n was 1, I would just add 1 2 pi. if n was 2, I would add 2 pi's, which would be 4 pi. Does that make sense? So if your answer, if I don't give you a restriction and I say find the solutions to your trig function, and I don't give you any restrictions, you're going to find your answer. Remember, you're solving for x, which means you're going to find your angle. Okay? So you're going to find your angle and then plus any revolutions. And for this answer, it's going to be plus 2 pi. All right? You guys got to try.
All right, so the first thing, ladies and gentlemen, that I want you guys to remember on, again, when you're solving trigonometric equations, first of all, don't be confused with the trig. Just think of solving the equation just with like x's. Okay, so if we were going to solve in this case, guys, we'd undo addition first. We would undo division next. And then we'd undo squaring, right, by introducing the square root. And remember, when we introduced the square root, we would include plus or minus. And then I could simplify that to the square root of 3. I'm sorry, that's 4, right? 4 over the square root of 4, which is 2. Would everybody agree with me on that? So in the same thing, guys, that's all I'm doing here. I mean, I'm doing the same process. Just make sure you simplify the square root, though, because if you guys look at this, that's not really going to help us out anywhere. So when you introduce, cosine of theta equals the square root of 3 over 2. Because again, what we're doing is we're looking for the angles where the cosine is equal to the square root of 3 over 2. Well, if we're looking on the angles like based on the unit circle, we recognize this. We probably wouldn't recognize square root of 3 over 4, though, right? I mean, it's there. It's still the same thing. It's just not simplified. So now what we're doing is we're looking for all the angles. When I take the cosine of that angle, I get square root of 3 over, I'm sorry, plus or minus, right? Plus or minus square root of 3 over 2. And then I have my constraint 0 to 2 pi. So we're not using inverse function where we're just finding that one angle that fits within the domain. We're finding all of the solutions. So we go to our unit circle. I'm sorry, all the solutions between 0 and 2 pi, which is basically one revolution of the unit circle, right? Here's 0 to pi, here's 0 to 2 pi. So it's basically finding all the values when cosine is equal to the square root of 3 pi over 2. Now, the way that I like to do this, or at least the way that I understand the unit circle, is I know this coordinate point gives me that solution that I'm looking for. That answer is pi over 6. Correct? And then if I want to find where are all the other angles where cosine is either equal to a positive square root of 3 over 2 or negative square root of 3 over 2, well, they're all these angles are going to all have the same reference angle. They all have a reference angle of pi over 6. Yes, because basically what these angles are is just a reflecting over here, reflecting down, and reflecting down. So I'm not going to draw in all of these points, but you guys could say theta equals, we know pi over 6. Does anybody know what this angle is? 5 pi over 6, right? Because halfway around the circle is pi, or 6 pi over 6. Subtract pi over 6, you're at 5 pi over 6. This next angle is pi over 6 plus pi, which would be 7 pi over 6. And then this angle is pi over 6 short of 2 pi, which would be 11 pi over 6. So you could see your answer written like this. You could also write your answer in set notation, but just by using a set, and that's fine as well. You'll see that often on your quiz, like something like represented like that as well. Does that kind of make sense? Anybody have questions on how far the other ones? Yes?
If I said negative 5 over 6 and negative 5 over 6, is that fine?
Nope, because those do not fall within the restriction. So you have to stay, so 0 to 2 pi means all the angles have to be positive, right? Okay.
So for this problem, guys, it's going to be the exact same thing. Our main important thing, like I said, we have a square here. But exactly what we're going to do, let's just get our trig function by itself. So what I'm going to do is I'm going to get rid of this 1 by adding a 1 to both sides. So then I have 4 cosine squared of x equals a positive 1. Now, let's get rid of that 4, right? I'm going to undo addition, subtraction, undo multiplication by division. So therefore, I have cosine squared of x equals 1/4. Now, I need to get rid of this square. So this cosine of x, or cosine squared of x, means cosine times cosine. So to undo the squaring, we take the square root. Now, I have cosine of x equals, and please remember this, if you guys remember when we were looking at your test earlier, remember a lot of times I'd mark you guys down with that plus or minus. We have to make sure that we're keeping in mind, whenever we take the square root, when we're solving, we got to make sure we include the plus and minus of our problem. So at plus or minus, the square root of 1, remember this equals square root of 1 over square root of 4. So the square root of 1 is 1 over the square root of 4 is 2. So I have plus or minus 1/2. All right? So when I look at my unit circle now, now I have the 1/2 and negative 1/2. So I actually have 4 coordinates here. And if you guys remember, these 2 coordinates is radical 3 over 2, so your other point.
Yeah, 4 coordinates.
Yeah, 4 coordinates. A lot of answers, right?
Yeah, 4.
4 different answers. So then we look at, all right, well, let's write on, what exactly are all these angles that we're dealing with. First one is pi over 3. Next one is 2 pi over 3, right? Then we got 2 pi over 3, 3 pi over 3, 4 pi over 3, 5 pi over 3. Okay? So we got 4 answers now. Okay? Now, rather than writing down those 4 answers, I'm going to show you guys a way that we don't need to write down all. You understand how I got those 4 points? Remember, this is 3 pi over 3. If you look at pi over 3, 2 pi, 3 pi, 4 pi, 5 pi. I know it's not to scale. It's probably really bad and scratchy, but you guys can see that at least those are the angles. So, ladies and gentlemen, if my first answer is pi over 3, right? I know it's pi over 3 plus 2 pi n, right? Because we've kept on adding the coterminal angle. So I have here plus another 2 pi, plus another 2 pi, plus another 2 pi. However, one thing I notice is if you guys look at what's the distance from this angle to this angle. I know it's kind of chicken scratchy, but it's just pi, right? So if I just add pi, I get to that answer. And if I add pi again, I get back to my original answer, which would be my coterminal angle. So rather than just adding 2 pi for this one, I can just add pi, which will give me this answer. Then again, it'll give me back that other answer. So rather than writing 2 pi n for all 4 answers, all I really need to do is add pi to this first answer. Does that make sense? Yeah. It's a simpler way of doing it. And yes,
You're only going to have 2 answers.
yes, you only need to represent it as 2 answers with adding, because here I'm going to have my 2 pi over 3, and then all I need to do is add pi to get to there, add pi again.
So that's any time where you have a plus and a negative and a positive number of the answer.
Not necessarily. You're going to get some answers where once you notice is when you see your answers, you'll see that they are pi distance away. So then you might even be able to write one answer and just write it as plus pi. Or you might have 2 answers might be plus pi. So it's just going to kind of depend on what you'll just see, like when you look at your answers, just look at the distance between them and see if you can write it like that. But that is how you guys would write your answer right there. So that is your answers to that equation. All right?
Yeah.
Welcome. So what I have is the tan of x plus the square root of 3 equals 0. So what I'm going to do for this problem is we need to solve and find the values of tan of x. So what I'm going to do is we're going to have to isolate our trigonometric term. So the first thing I'm going to do is subtract the square root of 3 on both sides by the subtraction property of equality. Therefore, now I have tan of x equals negative square root of 3. So what I want to do to find the values of x that are going to make this equation true, what I need to do is I need to figure out what values of x are for tangent are equal when we have the negative square root of 3. So what I need to do is go back to my unit circle and decide when do I have a tan value that's going to be equal to negative square root of 3. So I'm going to go and use my first quadrant, even though I know that this is a negative point, but I'm going to use this so I can represent it around it because I remember my points in the first quadrant. And I hope that you do too, because I made some videos on these, and I expect students, by this point in time, hopefully have at least an understanding of
unit circle because we've been working with it so much. So what I'm going to do, remember tangent is y over x. So which one of these is going to provide when I put y over my x is going to provide a square root of 3? Well, what we notice is this goes to 1. This is going to have 1/2 over the square root of 3 over 2, and which is end up going to give me with 1 over square root of 3, which when I rationalize the denominator is not going to give me the square root of 3. So the next point I look at is what about the square root of 3 over 2 divided by 1/2? I can just cancel out to get me square root of 3. However, that's for the positive square root of 3. So when would this be a negative square root of 3? Well, if this angle is pi thirds, so the next angle over would be 2 pi over 3, which is going to now leave me with a negative 1/2 comma square root of 3 over 2. Okay, so that was going to be that point. Now you could also say, well, there's another angle all the way down here, right? 2 pi over 3, 3 pi, 4 pi, 5 pi over 3. But before we get into that, let's just write in down our one answer. So we can say that my value is equal to 2 pi over 3. Now what we notice is, from here's my first answer to my next answer, that distance you can see is halfway around a circle, which would be pi. And you can think, all right, so remember coterminal angles. If you add 360, you're going to get the exact same angle. So we could say that, well, you could add 2 pi r to this. But we have another angle here, and the distance from this angle to this angle is pi. Because remember, the period of the tangent graph or the tangent function, the period is pi. So therefore, all we need to do is just add pi, and we'll get every single value. So if I have this angle, I add pi, I go here, I add pi again, I get a new angle, add pi again, add pi again. So I'm always, by adding pi, I'm going to be going between these two angles, which are both going to be our solution. So it's important when looking at the tangent function that we make sure we include the period of pi. And we can just write 2 pi over 3, it was our first angle, plus pi times how many times we want to multiply, because remember there's going to be infinite many solutions as coterminal angle, or my angles can just keep on revolving. So there you go, ladies and gentlemen. Hope you enjoyed. Thanks. You guys wanted me to solve for x. So it says 4 cosine squared of x minus 3 equals 0. So to do a problem like this, we're going to have to remember our unit circle. Now for those of you that said, oh, why don't we use our unit circle and blah, 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 blah. Well, now it's going to come to a point, ladies and gentlemen, where we're not going to have the unit circle with us. So it's become very important that we can go back and kind of remember where our unit circle, what values we're going to have. So here I have 4 cosine squared of x minus 3 equals 0. All right? So I've been telling you guys, you need to make sure you have that unit circle memorized, because here's now coming to this point where we have to know these values of our trigonometric functions. And if we don't know the values, we need a way to remember how to find each one of those values. So the first thing we need to do, obviously, is we need to solve for our cosine of x. So first thing we do is going to add 3 to both sides. We're going to have 4 cosine squared of x equals 3 divided by 4. So right now I'm just using inverse operations. Then I need to solve for cosine of x, so I'm going to take the square root. So therefore I have cosine of x equals plus or minus the square root of 3 over the square root of 4. Remember, I can distribute that square root to just the top and the bottom. Therefore, I know that this is going to be just 2, right? So actually, I'll just say, so square root equals plus or minus the square root of 3 over 2. So what they're asking us to do is find the values when cosine of x is equal to plus or minus the square root of 3 over 2. So we need to go back and remember, when is the cosine value equal to that? Now let's just go back and remember our major points. We had the first one, which is 30 degrees, or pi over 6. We had 45 degrees, or pi over 4. And then we had 60 degrees, which would be pi over 3. So I'll write the coordinate points if you guys forgot them. And remember, these are all x, y, x, y. So out of those 3 points, when is cosine square root of 3 over 2? At pi over 6, right? So we could say x equals pi over 6. And then remember, when else would cosine of x equal pi over 6? Right, it's going to be this point right down here, right? And then, so if you know that this is pi over 6, this is pi away, right? This is going to be pi away from 2 pi. Remember, all the way around the circle is 2 pi, right? So it'd be 11 pi over 6, right? Because 5 pi over 6 would be over here, right? Because it would be 6 pi over 6. So 11 pi over 6 over here, which would be a negative square root of 3 pi over 2. But we're just looking for the positive value, so it'd be 11 pi over 6. Got it? So you guys have to remember, if anything, just remember these first three coordinates, because then you can relate them. Yes? What? Oh, you're right, actually. I'm sorry. You're right. It is plus or minus, right? So we need to do the negatives as well. So yes, 5 over 6 works as well. Sorry. So 5 over 6. And then this point right here, which would be 7 pi over 6. And do they give us a constraint on this one? Yes, they say between 0 and 2 pi. So these would be your only values, right? And then remember remember what we could do if they didn't give us a constraint. Remember that plus 2 pi n, which would be coterminal angles that you could do, right? Yeah. To solve a problem like this, what we're going to do is we're going to find our values of x, and we want to make sure we solve for it. That's going to be on within the range of 0 and 2 pi. All right, it has to be within that interval. So again, like we worked on before, we have to evaluate for our cosine function. So we need to isolate it, right? So let's use our inverse properties to isolate. So we add 2 to both sides. So I get square root of 3 times cosecant of x equals 2. Then, to undo multiplying by the square root of 3, I'm going to divide by the square root of 3. And I get cosecant of x equals 2 over radical 3. Now, before I go and rationalize the denominator, which we've ingrained on us, right? Automatic, got to rationalize it down. Before we get to that, we can actually work another step. Yes?
I was going to say, isn't the square root supposed to be on top of the bottom? Like, you can't have a square root on the bottom.
Right, so we'd rationalize the denominator. But before we just automatically rationalize the denominator, let's take a look at our unit circle. Okay? And remember, we're going to want to evaluate this by using the coordinate points on the unit circle. And ladies and gentlemen, we talked about finding the coordinate points on the unit circle. We said that the cosine of any angle on the unit circle is going to represent the x-coordinate of that point. The sine of that angle equals y. And the tangent of an angle equals the ratio of y over x. Right? Do you guys remember doing that? And we just said, oh, the sine of this angle, and then you just found the x or the y coordinate, right? And if tangent, you found the ratio. Well, here we're finding cosecant, right? So how is cosecant going to be related to sine? Because if I was going to pick on the unit circle, I could easily find what the y coordinate is. But finding the cosecant is a little bit different. So remember that cosecant of theta equals 1 over y, right? These are reciprocals of each other. So rather than trying to find the angle x that represents the 1 over y coordinate, let's just change this to the y coordinate. So how can you change, if this is written as 1 over y, how can we change it as y? Well, those are just reciprocals of each other, so we just reciprocate. So therefore, I could say, if cosecant of x is equal to 2 over radical 3, that means the sine of x is equal to square root of 3 over 2. Does that kind of make a little sense? And now that's a lot easier to do, right? Because now we know, oh, what values of x are equal to when the sine value, which is y, is equal to square root of 3 over 2. And that's a little bit easier from what we learned. So therefore now, we just need to figure out when is sine square root of 3 over 2. Well, there's 2 points. At this point, we have 1/2 comma square root of 3 over 2. And at this point, which we have negative 1/2 comma square root of 3 over 2. So now we just need to know and remember, what are those 2 points? Well, our first point, and remember, we're only finding the values within our interval of 0 and 2 pi. So our first value is x equals pi thirds. And the next point is going to be 2 pi thirds. Okay? None of these other points down here when sine, because sine would equal negative square root of 3 over 2 for any other of those points down in the third or fourth quadrant. So those are going to be your 2 solutions. Yes?
So it's only the right hand, like half of the unit circle that deals with cosine, and the rest is like on the top half. Like from 0 to 2 pi is for.
No, I mean, we could have, this problem could have been negative. Like if I would change this to this, a positive, then this whole problem would have been negative. And that means we would have found the negative sign, which would have been your points down here, which would have been your angles down there.
So it can be between, as long as
Your answer just has to be between 0 and 2 pi.
Okay.
All right, that's because that's the interval that I wrote in here. Sometimes we don't put a restriction on it, and I'll show you how to do those when you don't have a restriction. But here, I'm just restricting your answers between 0 and 2 pi. Okay? Any else questions? Good. Ladies and gentlemen, now what we're going to do is we're going to introduce you to solving trigonometric equations. Okay? When solving trigonometric equations, you guys have all the information you possibly need. The first thing we're going to do is solve. I'm sorry, we're solving for x. Okay? So, just like you guys have done before, we're going to solve for x. So I'm going to add a 3 to both sides. Tangent squared of x equals positive 3. Right? Are we good?
Yep.
Okay. The next thing is we don't want to solve for we got to get rid of this tangent squared. So I'm going to take the square root of both sides. Please remember when you introduce the square root, though, we have to make sure we include plus or minus. Okay? So now we're trying to find the values of x. Now, if you guys remember, when we're saying the tangent of x equals, so forth, I say, what is x? What does x represent? Does anybody remember? What is x supposed to represent? Yeah, that's all? Yeah, it represents theta, which represents the angle, right? We're looking for an angle. So just to note, when you guys are doing the unit circle, we're looking for an angle. We did this in your last test. We talked about finding the angle, finding the x. And one thing we talked about was using inverse tangent. You can write this down if you like to. It's not really going to help you out as much, but this is what we previously did. Right? Is we talked about solving tangent of inverse, and we did like plus or minus x. And we'd say, what angles would produce that? And if you guys remember when we did this, when I said solve for x, we used the inverse tangent to solve, right? But there was a problem with this, because the restrictions for tangent inverse had to be between negative pi halves and pi halves, correct? So if you were to solve using that method, tangent inverse, there's only going to be 2 angles. Now, first of all, how do we even know which angle are we going to be using? Well, there's only 3 possibilities for tangent. We have tangent of pi over 6. You have 45 degrees. Or you have pi over 3 degrees, or pi over 3 radians. Now remember, the tangent of an angle represents y over x. So if I take y over x, is that going to give me plus or minus the square root of 3? No. If I put y over x, will that give me the square root of 3? Yes. So what was this angle again? 60 degrees, or we're just going to be using radians for your answers. So that's pi over 3, or 60 degrees. So it works in that one, but then it also would have to be in this one, right? Correct? So to solve this method, we'd equal pi over 3 and negative pi over 3. But now that's what generally you guys would do before, okay? However, in the problems for tonight's homework, I am going to give you a constraint that I want the answer to be between 0 and 2 pi. I want to find all the answers, all the angles that are between 0 and 2 pi.
So since you have a bracket on 0, it could be 0.
It can equal 0, right? But does the coordinate point 0 make tangent square root of 3? No.
So wait, how does
Well, first of all, the angles have to be between 0 and 2 pi. So does this negative work?
No.
No. So guess what? I'm actually not going to think about this. Even though that tangent inverse is OK, my constraint is asking me to do something different. So I'm just not going to worry about that. It's OK if you wrote it down. There's nothing wrong with it. But I know that a negative is not going to work.
So I have a question.
Yep.
You said pi over 3, the coordinate points is 1/2, and
Well, let's look at it. Tangent of pi over 3. is equal to y over x, right? Which is equal to square root of 3 over 2, comma, 1/2. If you were to multiply by the reciprocal, right, which I've done like over and over, you're left with square root of 3. Now, right. So there's my one angle. So is it OK then for math purposes that I erase the other angles that I have up there, not to confuse us?
Yeah.
Is that OK? Because we know they're not a part of the answer. We only have one answer, one angle. And I know since it has to be between 0 and 2 pi, the negative's not going to work either. OK, here's my one angle. That is when that gives me square root of 3, right? However, the answer for all the angles between 0 and 2 pi, not only when is it square root of 3, but also negative square root of 3. So I want to find all the angles that are going to have the same coordinate points, correct? So what I want to do is look at my reflections. Again, I have not used the unit circle. The only thing I knew was the first quadrant in the unit circle, which helped me identify this. Now, if I reflect this about the y-axis, I get this coordinate point. If I did y over x, would that give me plus or minus square root of 3? It'll give you negative. Yep. If I reflect this now over the x-axis, would I still have negative square root of 3 or positive square root of 3 when I did tangent? And if I reflect it again, I would have negative. Sorry, that'd be a negative over negative, which would be positive.
That's not a negative over negative at the bottom, is it?
No, that's positive. There you go.
But that would still be negative.
Right?
The quotient. Yeah, the quotient.
So do you guys see? Yes. Do you guys see all of these give me either positive square root of 3 or negative square root of 3 when I do the tangent of their points? Does that make sense? Right? Now, all we got to do is figure out what the angles are. Well, if this one was pi over 3, if I reflect it back over, the next one's going to be 2 pi over 3. It's going to be 2 pi over 3. And you guys can confirm that on your unit circle if you want to. If here, to go from here is pi over 3, if I reflect it over, then how far is it over here? Well, yeah, it's negative pi over 3, right? But remember, our angles aren't going to be negative, right? They're always going to be positive. Huh? Well, OK, so we know the distance is pi over 3, right? We're going by thirds. All the way around the circle is how far? It's 2 pi, or 6 pi over 3. If I'm 1 pi short, how far am I? 5 pi over 3. And then if I was just to reflect that over, how far would this be? 3 pi over 3. Add on 1. Remember, guys, the reference angle. Remember the reference angle. The reference angle is the distance from the x-axis to the terminal side. This distance is how far? Pi over 3. This distance is pi over 3. This distance is pi over 3. So let's talk about it again. Halfway around the circle is pi, right? Which is equivalent to 3 pi over 3. If I have to go an extra pi over 3, where am I at? 4 pi over 3. So the number of solutions between 0 and 2 pi for this equation is 4. And those solutions are pi over 3, 2 pi over 3, 4 pi over 3, and 5 pi over 3. OK? Do you guys see how this is different? I'm just trying to make sure this is a little bit different. It's related to what you guys did in 4-8, but it's different because if you guys were to do that tangent inverse, you only would have got, well, technically you only would have got the one answer, right? The one answer that we actually would have had two answers. You would have had pi over 3 and negative pi over 3. But you guys can see, based on my new restrictions, that doesn't give you all the answers. My new restrictions are all the angles between 0 and 2 pi. Well, yeah. If you look at pi, that point is negative 1, 0. Take y over x, that gives you 0. We're trying to get, when you do y over x, you need to get either square root of 3 or negative square root of 3.
Oh, sorry, I thought I could be able to do this within the restrictions.
Well, yeah, but it has to be an angle that makes the equation true. Yes, it is. It has to be one of the problems that make the equation work. Tangent. It has to be an angle that satisfies tangent.
Okay.
Because what's tangent of pi? Tangent of pi is what?
Pi over x.
0, right? Is 0 equal to plus or minus square root of 3? No. So that's why it doesn't work. OK, so let's go over this y equals 3 to the y equals of 3 of x equals 1. So the main important thing to do a problem like this, I believe they're asking us to find all of the solutions. So first of all, I need to figure out, well, when does tan of x equal y? Now again, tangent becomes a little bit more difficult when looking at the unit circle, because we need to remember, when I go and look at my points on the unit circle, remember tangent of theta is your ratio of your y coordinate over your x coordinate. So we're not looking for the point 1. We're not looking for an x or y coordinate that's 1 up there. We're looking for when is the ratio of my y and my x coordinate equal to 1. So I look at my first quadrant. And by knowing these points of the first quadrant for this first important points, I can see that there's only one ratio of y coordinate over x coordinate that's going to produce 1. It's going to be this angle right here, because square root of 2 divided by 2 divided by square root of 2 divided by 2, that obviously just equals 1. So we need to remember, what is that angle? Well, that's pi over 6. So this angle is pi over 4. So therefore, I can say in this case, 3x equals pi over 4. Now to find, again, all solutions, you treat this just the same as finding it with not a multiple angle. Then I just divide by 3. X equals pi over 12. I'm sorry, shoot. For finding all the solutions, right? OK. So, I forgot a couple steps. So here, it works for pi over 4. But is that the only time when tangent equals pi over 4? I'm sorry, equals positive 1. No, there's this other angle over here. Well, we know over here, my x is negative. Down here, my y is negative. But if I do a direct ratio over here, that's negative square root of 2 over 2, comma, negative square root of 2 over 2. So the negative divided by negative will still make it a positive 1. If that's pi over 4, 2 pi over 4, 3 pi over 4, 4 pi over 4, 5 pi over 4. OK, so therefore, I can say 3x equals 3 pi over 4, and 3x equals 5 pi over 4. Now, however, between my two solutions, you can see that if I say here's my first solution, well, to get to the next solution is just adding pi. To get to this next solution again, I add pi. And I can just keep on adding pi to get between the solutions. So rather than writing both of the solutions, I can combine this just to say 3x equals pi over 4 plus pi n. Because if I add n once, that takes me to this solution. If I add n twice, that takes me back over to another solution. So I can simplify this. I can simplify writing both those solutions like that. And then I can just divide by 3. So therefore, x equals pi over 12 plus pi over 3n. Now, if you guys were asked to find find the solutions between 0 and 2 pi, what you'd have to do now is add numbers of n. Now, this is the answer, because it just says find all your solutions. But if I said find only solutions between 0 and 2 pi, what I have to do is plug in numbers in for n and see how many times, whenever I find a number for n, see if that answer falls between 0 and 2 pi. For instance, let me just do 1. Let's pretend n equals 1. So x equals pi over 12 plus pi over 3, right? Because n times pi over, or 1 times pi over 3 is 1 over 3. Combine those, so I'd multiply by 4 over 4. So x would equal 5 pi over 12. Would that be a solution between 0 and 2 pi? Yes, because 0 and 2 pi would be 24 over 12, right? It's the same thing. 0 and 2 pi is the same thing as 0 is 24 over pi. So therefore, I could do it for, I could add n once. I could make n 2. See if you could do n 3 and so forth if you want to find it between 0 and 2 pi. But I'm just asking you guys to do it for all real solutions, so that would be your answer. So, ladies and gentlemen, when so far our problems that we've been dealing with have been kind of simple. They've already been kind of solved on one side and really just need to do some easy operations. Well, when I'm looking at something like this, we need to make sure, guys, whenever you're solving for an x or a y or any kind of variable, the main important thing is you got to get them on the same side, right? So the first thing I see I'm going to have to do is I got to get my tangent of x, right? I'm trying to solve for tangent of x. I got to get those onto the same side. So I'm going to subtract the tan of x from this right side to get over here. So now I have 3 tangent cubed of x minus tangent of x equals 0. Right? So now when I'm looking into my solving, one thing I notice is they both share a tangent of x, so I can factor it out. And all this tangent cubed of x means tangent squared of x equals tangent of x times tangent of x. So tangent cubed is going to just be another multiplied by tangent x again. So what I can do is I can factor out a tangent x. So I factor out a tangent of x, I'm left with 3 tan squared of x minus 1 equals 0. Does everybody follow me? Okay. So now, since I've factored out my tangent of x, now what I have is a zero product property, where I notice that I have two terms that are multiplied by each other to give me 0. Therefore, now I can rewrite this as tangent of x equals 0 and 3 tan squared of x minus 1 equals 0. Okay? So now I need to think about, when is tangent equal to 0? What values is that going to be equal 0 to? So I take a look at my unit circle, and I notice that this is going to be equal to 0 at 1 comma 0 and negative 1 comma 0. Why is it those 2 points? Because remember, it's y over x. You can't use these 2 points because then your x would be 0 when you'd have 2 undefined points. So therefore I can say x is going to equal, well, you have 0 and pi. So these are in relation of pi to each other. So I can just say pi n. And the other thing we noticed is this problem, they also said we have a restriction, right? Our answer has to be between 0 and 2 pi, right? So I'm actually not going to include that. We'll just say x equals 0 and x equals pi.
That means you can't add in because they're going over 2 pi.
Oh, see,
What gives you the yeah.
The restraint was in the the restraint was in the directions.
Oh.
If you read the directions, it says the answer has to be between 0 and 2 pi.
Yeah.
So now we got to go and solve this one. So if I solve this one, I'll add the 1 to the other side. So I have 3 tangent squared of x equals positive 1. Divide by 3. I get tangent squared of x equals 1/3. Whew. Got a lot going on, right? Now I need to undo that tangent squared, so I need to square root. So I get tangent of x equals plus or minus. Remember, this equals square root of 1 over square root of 3. So that's going to be 1 over radical 3. Plus or minus, right? We took the square root. Now, I'm going to rationalize the top and the bottom. So my final answer is tangent of x equals plus or minus radical 3 over 3. Now I need to determine which point is radical 3 over 3, right? So I need to remember tangent of your theta angle equals y over your x. It's your tangent of any angle on your unit circle. We're going to have our y coordinate over our x coordinate. So I need to determine what coordinates give me radical 3 over a 3, either plus or minus. Well, this point would be radical 3 over 1/2, right? And what you notice, I'm sorry, that's the other way around. Y is my x. So y would be my 1/2 over radical 3 over 2. So yes, when I do have a pi over 6, which is radical 3 over 2 comma 1/2, that point does give me that point, pi over 6, does give me radical 3 over 3. So therefore, I can now say my answer is x equals pi over 6.
Yeah, 4 different answers.
Then pi over 6, 5 pi over 6. Then our answer down here, 6 pi over 6, so this one would be 7 pi over 6. And then we have our answer over here, which would be just short of 12 pi over 6, or 2 pi, so that's going to be 11 pi over 6.
Yeah, that's why you can't add the plus pi.
Right, and we're not adding the plus 2 pi or the 2 pi n or plus pi n because it only says we only want our answer between 0 and 2 pi. Okay? That's it. So here we have 2 answers for that, and then our 2 answers for that. And that's it. That's how you solve. All right, if I'm asking you guys to solve by evaluating our sign, and it has to be, make sure it's on the interval of 0 and 2 pi. Now, when coming up to a problem like this, obviously, ladies and gentlemen, let's go back through our a review quickly of solving. We talked about this. 3x minus 5 equals 20. Right? To solve an equation like this, these are the first type of problems I gave you. It's pretty easy. You just use your inverse operations. Right? And that was the first thing you guys learned how to solve. And that's what the first common videos we talked about. Now, what happens if I give you a problem where it maybe looks like this? 2x squared plus 3x plus 1 equals 0. You guys can notice this is really the exact same problem, except I'm just not dealing with the trig functions, right? But I have a 2x squared plus 3x plus 1. So how do we solve something like this? You can't subtract the 1 and then try to solve for x. This process doesn't work when you have a squared exponent and you have more than one. And you have a squared variable and you have more than one. So we can't just use inverse operations. Does anybody remember what the special property that we have to use when we have factoring, right? And we have to use a factoring so we can apply the zero product property. So here, we cannot solve this like we did here. We have to apply factoring and the zero product property. So we go and look to factor it. And so one of them is going to be 2x, and the other one's going to be x. And then we just say, how are we going to add this up? Well, we can just kind of use a little guess and check and say 1 times 1 equals 1, and then times 2 equals there. Then once we know that we have one binomial times another binomial equals 0, we set them both equal to 0, right? And then now we can solve our problem. So therefore, you could say x equals -1/2, and here x equals -1. Does everybody follow me on doing this? This is algebra stuff. So now, guess what? We just need to do the exact same thing. But now we're just intertwining. Rather than just dealing with x, we're dealing with sine of x and sine squared of x. So the other techniques that we did before, just isolating the sign, we can't use anymore. We have to now apply a factoring technique. So I need to say what two terms are obviously going to multiply to give me 2 sine squared. So that means one of them needs to be sine squared of x, and the other 2 sine squared of x. And then both these two terms need to multiply to give you 1, right? So you just factor it like you would factor any other algebraic expression. Neither of them are squared. Sorry. Because 2 sine of x times sine of x equals 2 sine squared of x, right? They should not be squared. And then when you combine them up, you get 3 sine of x. 1 times 1 equals 1. We're all good. So now we can apply, once we have it factored, we can now apply the zero product property. So therefore, you can say 2 sine of x plus 1 equals 0, and sine of x plus 1 equals 0. So now you could say sine of x equals -1/2, and you could say sine of x equals -1. So now, again, going back, knowing your unit circle, we need to determine, our equation is going to be true for all values when the sine of x equals -1, or when our angle, we have an angle that's going to equal -1, or we have an angle when we take the sine of it equals -1, or -1/2 and -1. So we're going to take a look at our unit circle, and we say, all right, well, I think this one's kind of the most basic. When is my x equal to -1? Well, you have kind of these 4 coordinate points. Here's 1, 0. Here's 0, 1. -1, 0. 0, -1. So the only angle when sine is represented as -1 is going to be this angle all the way here, which is, does anybody know? There we go. Thank you. Not 3 pi over 3, 3 pi over 2. All right? Then we go and look over here, and we say, when is sine of x equal to -1/2? So therefore, that's going to be -1/2, which is the problem we've actually already done, which is going to be these two values right here. So therefore, x equals 7 pi over 6 and 11 pi over 6. So therefore, we have, for this equation, 3 solutions on the interval of 0 and 2 pi. OK? So obviously, secant and tangent are not reciprocals of each other. But to solve this, we need to get them to be the same. We need to either solve for secant or we need to solve by tangent. So what are some other ways that we've learned? Well, we've looked at our Pythagorean identities. And when looking at your Pythagorean identities, we know that secant and tangent are related to each other, aren't they? Yes. So obviously, guys, when thinking about solving, finding our answers, tangent is going to be what we're going to want to look for rather than secant. It's a lot easier for us to understand what the answers to a tangent are, because we know that tangent on the unit circle is your y coordinate over your x coordinate. Make sense? So I'm going to want to convert secant squared over to tangent. And I believe one of secant of x equals tangent squared of x. That is one of our Pythagorean identities. So if I want to solve for secant squared of x, what I would just say is secant squared of x also equals tangent squared of x minus 1. So what I'm going to do is I'm going to substitute in tangent squared of x minus 1 in for secant. So therefore, now I'm going to have all the tangents. Yes?
It's 1 plus tangent squared equals secant squared.
1 plus tangent squared equals secant squared?
Oh, yeah, that's right.
Okay. So it's already solved for me. So therefore, I'll just plug that in. I'll just plug 1 plus tangent squared in for x. So I have 2 times 1 plus tangent squared of x plus tangent squared of x minus 3 equals 0. Okay? You ever see why I did this? Now I have all tangents, which I can work with. Right? When I had secants and tangents, that kind of got a little difficult. But now I have all tangents. I'll use my distributive property. 2 plus 2 tan squared of x plus tan squared of x minus 3 equals 0. Well, here, what I can do is now I can combine my like terms. These are both tan squareds, so I can combine them, and I can combine these. So what I obtain is 3 tan squared of x minus 1 equals 0. Does everybody follow me? Any questions? Okay. Now we just simply need to solve for our tangent of x. So I'll add 1 to both sides. 3 tan squared of x equals 1. Divide by 3. Tan squared of x equals 1 over 3. Then, to get rid of the square root, I need to take undo by taking the square root of both sides, or get rid of the square, take the square root. So now I have tangent of x, and remember this equals square root of 1 over square root of 3. Square root of 1 we obviously know is 1. Square root of 3 is, we need to rationalize. So I have square root of x equals, remember when you take the square root of both sides, it's plus or minus 1 over radical 3. Well, ladies and gentlemen, we don't ever leave our radical on the bottom, so we rationalize the denominator. And we get is radical 3 over 3 plus or minus. Okay? So I need to figure out when is my coordinates on my unit circle, tangent of x equals plus or minus radical 3 over 3. When do my coordinates y over x equal radical 3 over 3?
5 or 6.
Okay, well, let's take a look, see if you're correct. So if I was going to have my unit circle, pi over 6 provides me this coordinate, radical 3 over 2, comma, 1/2. If that was my x coordinate and that was my y coordinate, to find tangent, I would have 1/2 over radical 3 over 2. If I was going to simplify this, those would cancel out. I'd equal 1 over radical 3. Simplify that again. Radical 3 over 3. So yes, you're right. Pi over 6 works. But then remember, guys, this is plus or minus. So it could be all the positives. So the other positive, down right here, and then the negative, right here, right here. So all of these points are going to work. So this is pi over 6, so we could say x is going to equal pi over 6. This point would be 5 pi over 6, 7 pi over 6, and 11 pi over 6. Make sense? Does everybody see why I use all the values, not just the positive and the negative? Because when you take that square root, you got to remember that plus or minus. Right? Any other basic questions? That's no?
I was listening.
I don't know. Do you have any questions?
Welcome. All right. So in this example, what I have is sine squared of theta minus cosine squared of theta equals 0. And what I'm going to do in this case is I need to go ahead and solve for it. So I'm going to use that a couple different ways. I'm going to look into applying some factoring, as well as using my identities to help me simplify. So the first thing I need to remember is sine squared of theta plus cosine squared of theta equals 1, right? So if I know that sine squared of theta plus cosine squared of theta equals 1, I can rewrite this. I can substitute one form in for another, and it doesn't really matter which function you want to solve for. Just to kind of make this easy, I guess, on myself, I will substitute in for sine. So I'll set sine by itself, so therefore I know sine squared of theta equals 1 minus cosine squared of theta. Now what I'm going to do is substitute 1 minus cosine squared of theta in for sine squared of theta. So now I have 1 minus cosine squared of theta minus cosine squared of theta equals 0. Well, now, as I go ahead and substitute, I have now 1 minus 2 cosine squared of theta equals 0. And now I can go ahead and solve. So I subtract 1, subtract 1. I have negative 2 cosine squared of theta equals negative 1. Divide by negative 2, divide by negative 2. Cosine squared of theta equals a positive 1/2. Now what I need to do is now take the square root. So I take the square root of both sides. And I have cosine squared of theta equals plus or minus plus or minus 1 over the square root of 2. Therefore, then what I'll do is I'll rationalize the denominator, which will be square root of 2 over square root of 2. So therefore, I have square root of 2 over 2. Remember, it's plus or minus. So when I'm looking at that, so that's just cosine of theta equals plus or minus the square root of 2. So remember, when we're looking at when is my function going to be, when is cosine of theta equal to square root of 2 over 2? Well, remember, on the unit circle, the cosine function for my angle is equal for the x-coordinate where my angle intersects the unit circle. So if we look at our three common points, we have square root of 3 over 2, comma 1/2. We have square root of 2 over 2, comma square root of 2 over 2. And then we have 1, comma half, comma square root of 3 over 2. And what we notice is, well, the only one of these coordinates in my first quadrant where cosine is equal to square root of 2 over 2 is my angle pi over 4. So what I can do to now remember to find all the values between 0 and 2 pi, because in this case what I'm going to do is I'm going to find all the values, but I'm going to start with finding all the values between 0 and 2 pi. Now if I look at kind of some reflections, over here it's the exact same point except now the x-coordinate is negative. But that's okay because if we're finding the values, it's plus or minus the square root of 2 over 2. Then over here, both coordinates are negative. And then over here, my x-coordinate is positive again. Now, the tricky part is determining
Well, all right, I see that all these are points, but what are their angles? Well, I know if from here to here is pi over 4, right? So we have all these different angles we need to figure out. Well, if here's pi over 4, that's 2 pi over 4. That's going to be 3 pi over 4. 4 pi over 4, 5 pi over 4. 6 pi over 4, 7 pi over 4. And this would be 3 pi over 4. So therefore, my solutions between 0 and 2 pi, so if I asked you to find the solutions between 0 and 2 pi, I would have theta is going to equal pi over 4 plus 3 pi over 4 plus 5 pi over 4 plus, what am I adding? I don't even know where that came from. Pi over 4, 3 over 4, 5 over 4, and 7 pi over 4. So there's your 4 solutions. So there's 4 solutions to this equation between the terms of 0 and 2 pi. However, what if I said to find all of the solution? Because remember, this graph continues. It goes on for infinite, right? So if I don't want to restrict my solutions just between 0 and 2 pi, how am I going to determine all of the solutions? Now, what we've previously, remember talking about, if I have my solution pi over 4, to find the next solution that's at that point, I would have to add 2 pi. But what's kind of cool about this, if you notice from here to here, well, now if I move from here to here, that's pi over 4. If I move that direction again, that's pi over 4. I move again, that's pi over 4. Add another pi over 4. That's going to take me to the next solution. And if you just keep on doing this, what you notice is every single time, if you start at your first solution, you keep on adding pi over 4, that takes you to every single solution. So it's much easier for me to write, if finding all the solutions, just to write pi over 4, because that's my first solution, plus pi over 4 times r, where r is going to represent how many times we can write it, which is going to be indefinite. So there you go, ladies and gentlemen. That is your solutions between 0 and 2 pi, and that would be your, all of your solutions. Thanks. In this example, I have sine squared of x plus cosine of x. Now, automatically, what I would want to do for this is try to see if I could factor. Unfortunately, sine and cosine do not have the same common terms. So I can't factor anything out. I can't solve for it, because which x are you going to solve for, right? Because then you're going to have a solution with the x, right? Think of that as like x squared plus y, plus y. You can't simplify it like that. So one thing I do notice, though, is I have a squared term. And whenever I have a squared term, I always want to think of applying my Pythagorean identities. Right? So sine squared plus cosine squared equals 1. So if I want to replace sine, try to replace them in terms of their same trig function, right? So therefore, I can rewrite sine squared as cosine squared of x. So therefore, I can write sine squared of x equals 1 minus cosine squared of x. So now I'm going to plug this in for sine. OK? Yes? Sine squared plus cosine squared equals 1. So I subtracted cosine on both sides. Huh? We are. That's the Pythagorean identity on page 354. I use that Pythagorean identity to rewrite what sine squared equals. So now I know sine squared equals 1 minus cosine squared. So I'm substituting in sine squared by applying my Pythagorean identity. All right? So now I have negative cosine squared of x plus cosine of x plus 1 equals 1. All right? Now, in this case, I don't really want to factor with a negative 1. So what I'm going to do is I'll factor that out. I factor out the negative 1. And then I can divide by negative 1. So now I have cosine squared of x minus cosine of x minus 1 equals negative 1. Huh? I did. I factored out the negative 1. You could divide both sides by -1. It's the same thing. But I factored it out so I could divide it. Why is it what? I took the negative and I factored it out. So that becomes now positive. That becomes negative. That becomes negative. Huh? Then I divide by -1. So that's a negative. That -1 I factored out, I divided it by -1. So then that remains the same because that's the product of those two. Huh? It was always -1. Yes. So I don't throw things at people. That hurts them. Because that's a +1. Yeah, I just rewrote it. All right, so now, oh, this is, okay. Sorry? Guys, if you just want to divide everything by -1, that's fine. Here, watch. Just divide everything by -1. It's the same thing. Same thing. I just factored it out and then divided it. Fine. Divide everything by -1. That becomes positive. That now becomes negative. That now becomes negative. So we're left with cosine squared of x minus cosine of x minus 1 equals -1. The exact same operation. Okay? No, we haven't solved for x yet. Right? So now, remember, we look at this and we say, all right, how am I going to solve for x? I have two x's. One's squared, one's regular. So to do this, I need to look into factoring. The only way I'm going to be able to do factoring is if I set it equal to 0. So to do that, I add the 1 on both sides. Now I'm left with cosine squared of x minus cosine of x equals 0. Now I have it set equal to 0. Now I can apply factoring. So to do that, I factor out a cosine. So I factor out a cosine. I'm left with cosine. Now I'm left with cosine of x times cosine of x minus 1 equals 0. Okay, Caroline? Now, since I have the product equal to 0, I can now say that the cosine of x equals 0 and the cosine of x equals cosine of x minus 1 equals 0. Okay? Everybody understand? Okay. So now we need to go back to our unit circle and determine when does cosine equal -1. Okay? Yes. Oh, it is. I'm sorry. So when does cosine of x equal 1, right? Yes? OK. So when does cosine of x equal 1? Well, obviously, Maggie, the first couple points that we learned was 1, 0, 0, 1, -1, 0, and 0, -1, right? So when does my x coordinate equal 1? When does x coordinate equal 1? X coordinate equals 1 at cosine of x equals 1 at 0, or at 2 pi, or the angle is 2 pi. All right. However, we also look at this. So we have our angle. Now it all kind of depends on what our constraint is. And actually, on this problem, the constraint is just to find all the values. So I just need to find all the values for that. Then the other one is my other angle is cosine of 0. So when does cosine equal 0? Well, cosine equals 0 at that angle and that angle. Well, that's pi halves, and that's 3 pi halves. OK? All right. So if I was going to go ahead and find my angles, I could write in there, so since there's no constraints, I can say that theta has to equal 0, right? But then plus 2 pi r. So I could say theta equals 0 plus 2 pi r. Well, obviously, 0 plus 2 pi r is just going to be 2 pi r. Then I go and look at when does theta equal 1. Well, theta is going to equal 1 at pi halves. But then I can just add pi to get to 3 pi halves, right? And then I can just add pi again. So theta in this case is going to equal pi halves plus pi r. Because the distance from one solution to the next solution is only pi. So I can just add pi to those two. OK? Cool. So those would be your two, that would be your two solutions that make that true. Yes? I'm sorry? Well, that's where cosine is equal to 0. Right? So cosine is only equal to 0. Cosine is only equal to 0 at pi halves and at this angle 3 pi halves. But the distance between pi halves, so what you could do, you could have done pi halves plus 2 pi r. And theta equals 3 pi halves plus 2 pi r. But why keep on adding circles to that and adding circles to this? Because the distance from here to here is pi. Then add pi again takes me there. Pi again takes me there. So if I just add pi to my one solution, it's going to give me both those solutions. Yes, Mackenzie? That is when my cosine of x is equal to 0. Because if you look at that, that's when the x-coordinate is equal to 0. So cosine x-coordinate is equal to 0 at that angle, which is pi halves. And then the next time cosine is equal to 0 is at 3 pi halves. And the distance between pi halves and 3 pi halves is pi. So I can just add pi to get to the next solution, and then add pi again to get to the next solution. Okay? The difference for this one, here's my angle. My cosine of x equals 1 at 0. But the next time it equals 0 is when I add 2 pi to it again. Okay? So that's why those two are kind of different. Okay? So, guys, they want us to solve for 3 secant squared of x minus 4. And remember, ladies and gentlemen, I told you, if you're having trouble and you get stuck, forget about the trig function and just worry about solving for x. And you might even want to do it solving for x just to make sure you're not missing anything out. Because I was looking at a lot of students' solution for this problem, when they didn't have my undivided attention, what happened was they started making a lot of the similar mistakes. If I add 4 to both sides, right, I get 3x squared plus 4 equals plus 4. Divide by 3, and I get x squared equals 4 over 3. Remember, from here, now I need to take the square root. So I'm getting x equals plus or minus 2 over radical 3. And like I said, I can simplify this. I'll go through that in a second. Let's just put it away and look at it. But what I want you guys to understand is don't forget your plus or minuses, right? And it's really, don't forget your plus or minuses there. So if I'm going to solve this, I'm going to do the exact same operations. I'm going to add 4, and I get 3 secant squared of x equals 4. Divide by 3. Right? To get rid of the squared, I take the square root. So therefore, I get secant of x equals, remember, the square root of 4 over 3 equals the square root of 4 over the square root of 3. So that gives me a 2 over radical 3. Now, a lot of you automatically want to jump into rationalizing the denominator, which is good. That means at least it's been drilled in. Sorry, that's plus or minus, right? That's good. That means it's been drilled into you. But be careful. Remember, we're solving for our secant. We still need to find what this value is. It's very difficult for me to be able to look at what is the secant value. It's much easier for me to find the cosine value, which is the reciprocal of secant. So rather than writing 2 over radical 3 and rationalizing it, what I would do is I'll just write it as cosine of x equals plus or minus radical 3 over 2. Okay? Now I need to figure out when is all the points when cosine is really plus or minus, or is really square root of 3 over 2. And there's going to be 4 coordinates, right, on your unit circle. So you have pi over 6, 5 pi over 6, 7 pi over 6, right? And 11 pi over 6, right? Pi over 6, 5 pi over 6, 7 pi over 6, 11 pi over 6. Go ahead and look at your unit circles, and you'll notice that the cosine value is either plus or minus radical 3 over 2 for those 4 points, correct? Okay? Now the one important thing, guys, that what you'll notice is we still need to find our values for x. So remember, if I'm going to write this in my simplest form, I could say radical pi over 6 plus what we said, 2 pi, right? You can say this point plus 2 pi, plus 2 pi, plus 2 pi. Then you can say this point plus 2 pi, plus 2 pi, plus 2 pi. And then you go to this point, and then to that point, and it gets very redundant. So if I'm going to simplify this answer, if I say this answer, and I just add pi to it, if I just add 1 pi, I get to this answer. If I add another pi, I get back to the another answer. So I don't need to add 2 pi to all these, because just by adding pi gives me my other answer. Does that make sense? So what I can do is say, instead of saying all 4 of these answers plus 2 pi n, that's very redundant. I don't have to do that. A simpler way I could say that is just say, that's like a triple equals, pi over 6 plus pi, and then how many times are you going to add pi? Well, I could add it once, twice, 3 times, 4 times, infinite many times, right? So we'll use it as n. My other answer could be 5 pi over 6 plus, and if I add pi to this answer, I get to my other solution. So I can get pi n. Anybody have any questions on that? Yes?
Would it be wrong if we use our form?
We're going to be looking for simplified answers, so yes, it is going to be something marked on. Yes?
So, if I wrote 2 pi n, that would be wrong.
For this answer, you can do simplify it more. So yes, I would work with kind of you on getting to simplify. Yes?
But the whole point was to get it back to its original points.
You are. Think
That's
about
not
it.
its original point, though, if we do that.
What, pi over 6?
No, I mean, just plus pi.
But if you get plus pi once, it gives you to another solution, which is okay. And if you add it again, it's still going to get you back to your other solution. What we're doing, we're not trying to always get it to all the solutions. What we're trying to do is we're trying to name all of the possible solutions. So you just want to make sure whatever your answer is, names all of the possible solutions. Okay?
So, basically, guys, if you get stuck with this, what I would recommend doing is just write this without the cosines. Okay? And if you look at that, one thing I notice here is that when you're doing it this way, I notice, well, the first 2 term is squared, and the second 2 term is squared. So therefore, I possibly could have 2x, let's see, and they get to 1, so that would be minus 1 times 2x minus 1, which is what we call a perfect square trinomial. And let's make sure, does that work? 2x times 2x is 4x squared. Negative 2x, that's negative 4x. Negative times negative is a positive. 2x minus 1 squared equals 0. So that is my factored form. But we're obviously not factoring with x's. We're factoring with cosines. So therefore, I will write this as 2 cosine of x minus 1 squared equals 0. Now, ladies and gentlemen, I need to solve. So I root both sides. Yes, you can introduce the plus or minus, but 0 is not positive or negative, so it doesn't really matter. So you have 2 cosine of x minus 1 equals 0. Cosine of x equals positive 1/2. So now we need to figure out, well, what are the values then when cosine of x is equal to 1/2? So we go to our lovely unit circle, and we say, all right, well, in the first quadrant, cosine is equal to 1/2 at the angle pi over, anybody? 3. OK? So when else is cosine positive? Well, we know that cosine has to be positive in the first or the 4th quadrant. Now, again, I keep on forgetting to write my constraints here, but it has to be between 0 and 2 pi. So we can't go negative. Like, remember when we did inverses, we had to go like negative, right? Or like with sines and tangents. In this case, we can't go negative. We want to find all the solutions that are positive. So it's only positive then also in the fourth quadrant, where the reference angle is pi thirds. So what is this angle then? It's pi thirds short of 2 pi over 3, or 12 pi over 3. Starts with a E, rhymes with 11. 11, right? Yes, you got it. You didn't think I was funny. So our answer is x equals pi over 3, and x equals 11 pi over 3. Huh? No. Oh, wait, not 11 pi over 3. I was thinking 11 pi over 6. Why don't you guys say anything? It's 5 pi over 3, right? 6 pi over 3. Why was I saying 12? I don't know. You guys messed me up. Blame it on you guys. Yes, it is 5 pi over 3, not 12 or 11.
All right. So to do a problem like this, and what we've previously discussed, ladies and gentlemen, is finding problems, right? What we previously did was using inverse operations, right? You took your trigonometric function and you just undid what was happening to it, and then you're fine. Well, again, when you have a problem that you're kind of like, I don't really know what to do yet, it's very helpful, I think, a lot of times just to write it without the trig functions. So let's just write that as x to the fourth minus 4x squared equals 0. So if I asked you guys to solve this, right, in your Algebra 2 class, what would you have to do? Does that remember? Yeah, you'd have to look in the factoring, right? You can't just say x by itself and do everything else. You have to apply factoring, right? So if you're going to do a factoring problem like this, what you would do is you would factor out an x squared, and you'd be left with x squared minus 4 equals 0. Then, once you have a product equal to 0, that's why we love doing factoring, because once you have a product equal to 0, you can apply the zero product property, which states x squared equals 0 and x squared minus 4 equals 0. Therefore, you could say x equals 0, and then here x equals plus or minus 2, right, as you solve for each one. So that's how we do it with algebra. Now we're just throwing in a little trick. So when we look up here, all right, what do you guys think we're going to want to factor out? Cosecant squared, right? So you factor out cosecant squared of x, and you're going to be left with cosecant squared of x minus 4 equals 0. Now we have a product equal to 0. So we say cosecant squared of x equals 0, and cosecant squared of x minus 4 equals 0. Well, this just equals cosecant of x equals 0, right, as you solve. And then here, we add 4. Cosecant squared of x equals positive 4. Take the square root, and you can say cosecant of x equals plus or minus 2. But remember, rather than dealing with the cosecant, we don't want to deal with the cosecant when we're trying to find the values, right? We want to deal with the sine. So if cosecant of x is plus or minus 2, that means the sine of x equals plus or minus 1/2, right? What? Where did I lose you? Do you understand how I factored it? Did you understand it? Did you see how I factored this?
Yeah.
Okay. So all we're doing is we're simply factoring that out. Then you apply your zero product property to both terms. And now we're going to go and set to solve. Now the same thing, rather than looking at cosecant of x equals 0, let's take a look at when sine of x equals 0. So now I have all these values that sine equals. I need to find the theta that's going to make them true. So I create my unit circle, and I say, when is sine equal to 0? Well, at this point, we have a point 1 comma 0. That's where sine's equal to 0. And then when is sine of x, what angle, when I take the sine of it, is going to equal plus or minus 1/2? Well, at this angle, I have square root of 3 over 2, comma 1/2. At this angle, I have negative square root of 3 over 2, comma 1/2. Here, I have negative square root of 3 over 2, comma negative 1/2. And at this angle, I have square root of 3 over 2, comma negative 1/2. So I have all these different points that my sign value is either at 0 or at plus or minus 1/2. So now what I simply need to do is just list all of those values. So therefore, I can say x is going to equal the angle 0, pi over 6, which would be this angle, 5 pi over 6, which is this angle, 7 pi over 6, which is this angle, and then 11 pi over 6, which is that angle. So therefore, there's multiple solutions that make this equation true. Yes?
Why didn't it also equal the point at -1 and 0?
It could, actually. I'm sorry, I missed that. Yeah, yes. At pi would also be a solution as well. Thank you. Because that's going to be your point at -1, comma 0, right? And as long as it falls within our constraint of 0 and pi, we're fine. Yes?
But didn't you say that sine was when you did cosecant to sine, wouldn't that be 1 over 0, not 0?
Yeah, no.
Oh, I thought that was like undefined.
Well, let's see here. So you have cosecant of x equals good point. Yes, that would be 0 over your radius, or 1 over 0 over 1. So yeah, actually it would be undefined. It'd be undefined at 0. So therefore, sine of x would be 1 over 0, which would be undefined. So yeah, actually, good point. I didn't even I missed that. Thank you. Well, as I said, I didn't go through this problem before. So yes, that actually would be undefined. So therefore, that actually, these would not be your values. Good point. Thank you. Good job, Nico. Good investigating. So for those of you that were not here, when we're doing this, all we're doing is looking into solving our equations. All right. So for solving this equation, what I'm simply want to do is I need to solve for my x. Now remember, guys, when you have like one x, it's pretty easy just to get that trig function with the x by itself. But here I have multiple of my secants. So one thing that automatically triggers in my brain is to start thinking of factoring. So when I'm going to want to factor, I'm going to want to make sure I get all my terms over to this left side, and I can factor set it equal to 0. So therefore I have secant squared of x minus secant of x minus 2 equals 0. Now, some of you might be a little bit, kind of vague to see how you would factor this. So what I would recommend is to eliminate or just forget about the secants for a second and just see if you could factor this as it is, or this trinomial as it is there, okay? And when you do that, what you guys will notice is x minus 2 times x plus 1 equals 0 when you factor it. All right? And the next thing is, remember, guys, you got to remember the zero product property. When we have these two multiplied equals 0, we can set both of these equal to 0. Okay? So this is what we do. This is what we've done before with older algebra. Now, all we're doing is we're going to do the exact same thing with the trig. So what I notice is I can now factor this to secant of x minus 2, secant of x minus 2, and then secant of x plus 1 equals 0. Okay? Add them up. All right, so now what I want to do is I want to set them both equal to 0. So I have secant of x minus 2 equals 0, and secant of x plus 1 equals 0, right? But ladies and gentlemen, when we're trying to find our values for secant, it's very difficult for us to figure out what secant, actually let me solve this first before I go into that. So then I'll solve. So I have secant of x equals positive 2, and secant of x equals negative 1, right? Well, how do I figure out what the secant is? It's pretty difficult for us to do this. It's difficult for us to do cosecant, and it's difficult for us to do cotangent. So what we can do is remember what our reciprocals are. That remember, cosine is the reciprocal of secant. So I can say then that use the cosine is equal to the reciprocal of 2 over 1, which would be 1/2. And cosine of secant of negative x is still going to be negative 1. Does everybody see why I did that and how I did that?
Yeah.
We can, but it's very difficult to find what secant is on the unit circle, right? We know cosine is our x value, our sine is our y value, and tangent is y over x, right? We know those kind of two are easily, and we also know the unit circle. So if I don't, secant's kind of hard for us to visualize where it is on the unit circle. So what I can do is, if I rewrite it as a cosine, then it's now easy for me to see, oh, okay, I know cosine 1/2 is on the unit circle. I know cosine of negative 1 is on the unit circle. Make sense? So just remember, because secant and cosine are reciprocals of each other. So now I need to figure out, or remember, where is cosine of 1/2? And I don't think I wrote this, but we have to be between 0 and 2 pi. So I write this up.
That's a good circle.
Thank you.
Can it be pi over 3, 5 pi over 3?
Well, let's see where 1/2 is. I'm sorry. 1/2 would be at this point. 1/2 radical 3 over 2. And it's also at this point, which is
5 pi over 3.
1/2 comma negative radical 3 over 2. Well, this angle, like I said, is pi over 3. And that angle is 5 pi over 3. So you could say x equals pi over 3, 5 pi over 3. And then where does cosine equal negative 1/2 or negative 1? Well, negative 1 is only at this point, which would be at pi.
Pi. It's at pi.
How come you never had pi?
Hey, can we have like some pie?
Does that make sense? Does anybody have a question on this?
Chocolate pie. Did you just say chocolate pie?
Does anybody have any questions on this?
No, I get it.
In a serious, non-chocolate pie manner.
I get it.
Thank you.
You good?
Now, we recognize this, all right? And again, we're evaluating, looking for the value. Now, the main important thing, guys, like, first of all, we don't have a calculator, right? So we know we can't evaluate for the cosine of 37 degrees, and we know we can't evaluate for the cosine of 8. Same thing for sine, right? So we know we have to do something to change this so we can actually find the value, correct? And we kind of recognize this. Hopefully, once we do more and more of these examples, we're going to recognize this is a pattern that's written on the board as well as our formula sheet, which is a sum and difference formula, right? So now we just got to use process of elimination. Is this the sum and difference of the tangent of 2 angles?
No.
No. Cosine of 2 angles? Like, look at the cosine of u and v. Yeah. This looks like it's the sum, right? So this is the same thing as cosine of 37 degrees plus 8 degrees. Now again, per our first problem in class, we don't do this, right?
No.
We're not going to do that. But guys, using the order of operations, like, we can just add these together. Cosine of 45 degrees. And we say, oh, that's a lot easier. Square root of 2 over 2. Right? That wasn't that bad.
Wow, that was easy. 3 steps.
All right, let's do a process of elimination. Does it look like the tangent of 2 angles? No. Does it look like the cosine? Yes, right? So you can see that this is a cosine formula. Basically, this is your u, and that's your v. And therefore, if we're adding inside the formula, that means we are subtracting. So this is really cosine of pi over 12 minus pi over 12. So 5 pi over 12 minus pi over 12 is 4 pi over 12, which can also be reduced to pi over 3. Do I know the cosine of pi over 3? Pi over 3, 1/2. Okay? So in this example, guys, we have an expression. All right? Now, I know my cosines don't always look great, so sometimes we'll put these in parentheses. But either way, we don't have a calculator. We haven't used trig with calculators, ours. We haven't done any of that. So we have no idea how to evaluate the sine of 93 degrees, the cosine of 3 degrees, or anything like that, right? We have not even discussed anything in that regard. However, I do recognize something here. This does look like some kind of formula that is written on the board that's in my notes. Does it not? Yeah. So which one? Let's do a process of elimination. Is it the tangent formula? No. Is it the cosine one? No. What is it? It's the sine formula. Now, is it for the sum of two angles or the difference of two angles? The difference. Since you're subtracting, it's the difference. So literally, if I come to this problem, I look at it, I recognize what the relationship is. This is how long it takes me to solve this. This is really the sine of 93 degrees minus 3 degrees. And again, remember the first problem we did today, the square root of 9 minus 4? Right? You can't distribute, but can you simplify these right together? So this is the sine of 90 degrees. Sine of 90 degrees is 1. Done. So, but again, guys, we see the sum and the difference of two angles. So let's apply the formulas that we have, right? I mean, you're going to have access to them. So the sine of x plus 2, that's just going to be sine of x cosine of pi halves plus cosine of x sine of pi halves. Yes? Yes. Now here, notice the subtraction. Remember I talked about this. This is where people make mistakes. So use a bracket. My recommendation. Now let's do this one. So this is sine of x times cosine of pi halves minus cosine of x sine of pi halves. Now, you guys could probably distribute the negative and erase some things, right? Just so people can see how I go from one to the other, I'm going to actually spend the time and rewrite everything. I would not recommend you guys do that. I would just use your eraser so you guys can kind of see. But I want to show people that you distribute that negative. Because if you don't use the brackets, most people forget to do that. So now we have this huge equation, right? But now let's see if we have like terms or if we have terms that will maybe add to 0. And you can see that these two terms are exactly the same, but one's positive, one's negative. These terms are exactly the same, so we can combine them. Just like x plus x is 2x, cosine of x sine pi halves and cosine of x sine pi halves is going to be 2 cosine of x sine pi halves. Now, can we evaluate for the sine of pi halves? Yes. Right, the sine of pi halves is, carry the 1. It's 1. And then we can divide by 2. Cosine of x equals square root of 3 over 2. So really, is actually solving it that actually hard? Because when is cosine of x equal to 3 halves? All the solutions. X is equal to pi over 6 and 11 pi over 6. Because cosine is equal to square root of 3 over 2 here and here. So here's your two solutions. So the only way to keep on getting these solutions is I have to do a whole revolution, which would be adding 2 pi in. So in this case, I have tangent of 7 pi over 4 plus 5 pi over 6. So I won't expect you guys to write this first term down, but you guys can see this is two angles, u plus v. Right? So couldn't I just kind of like treat this by like taking the formula for tangent and then plugging in those angles in replacement of u and v? Yes? Now notice in the formula,
7 pi over 4 plus 5 pi over 6. Notice in the formula, when you're adding two angles for tangent, you add in the numerator but subtract in the denominator. So this is the tangent of 7 pi over 4 plus tangent of 5 pi over 6 all over 1 minus tangent of 7 pi over 4 times the tangent of 5 pi over 6. OK, now when you guys are doing, when you guys are going to be showing your work, what I'd like you guys to do is at least show me this step for your quiz. All right? Can we just try to show this step? I know it's a very basic step, but I'd like you guys to take this extra step here and showing me this. Because now, this is basically just taking the formula and making sure that you can show me you know the formula. That's all it is. You're just basically knowing, OK, I know which formula it is, and I know what the angles are to plug it in. Then the next one is evaluating based on the unit circle. Now, to evaluate the unit circle, I think it's going to be helpful to know the quadrants. 7 pi over 4 is in the fourth quadrant, and 5 pi over 6 is in the second quadrant. What do we know about tangent in the second and the fourth quadrant? It's negative. That's important. So all these values are going to be negative. Talk about like some issues that are going to be coming up, right? Now we need to know what is 7 pi over 4. Hopefully, guys, this is what I'm talking about. Evaluating the unit circle should be not something we should be able to do like this. 5 pi over 6, that is going to be a negative square root of 3 over 3. Again, this is all coming from the unit circle, which we've already covered in this class. Now, sometimes since this is minus this product, I'll put it in parentheses just to make sure that I remembered to group those together. OK? It doesn't really matter, but sometimes that can be helpful. All right, so let's go ahead and simplify this. So let's do -1 minus the square root of 3 over 3 divided by 1 minus the square root of 3 over 3. OK, now they look very similar, right? Look very similar. The only difference is that's a negative, that's a positive. So should we just divide this out and say it's -1? It's tempting, isn't it? Very tempting. But we can't do that, guys. You can't apply the division property. These are not exactly the same expressions minus a negative. So what we want to do, though, is we notice that we have fractions within fractions. And we actually had a name for those types of functions. Does anybody or fractions? Does anybody remember what types we call? It was in chapter 3. Starts with the C. Complex, right? Do you guys remember how we got rid of complex fractions? One of the methods? Yeah, well, no, we didn't rationalize the denominator in that chapter. We are going to rationalize, but not right. How do we get rid of the fractions? Not so much the reciprocal yet. We identified the LCD, and we multiplied everything by the common denominator. So let's look at these fractions and the fractions. What is the common denominator of all of my fractions? 3. So just multiply the top and the bottom by 3. When doing that, I now get So now I get a -3 minus the square root of 3 all over 3 minus the square root of 3. Now, technically, we'd want to simplify this by rationalizing the denominator. So now we'd want to rationalize the denominator. OK, now when you guys, I am going to kind of fallen out of room, so I'm going to continue this over here. So when you do multiply this, I would recommend doing this, guys, individually for the numerator. So this is going to be a -9 minus 3 square root of 3 minus 3 square root of 3 minus 3. Now the denominator shouldn't be that bad because that's just a difference of 2 squares. Right? When you multiply out a difference of 2 squares, you square the first 2 terms, which is 9, and you square the last 2 terms, which is -3. OK, now we can simplify this a little bit more. negative 12 minus 6 square root of 3 divided by 6, which equals negative 2 minus the square root of 3. What I do in this problem is I recognize I have a sum of two angles. So immediately, the first thing I do is like, well, let me apply that formula. So this would be the sine of alpha times the cosine of beta plus cosine of alpha times the sine of beta. Are you guys OK with that? That's just the formula, me just applying the formula all over cosine of alpha, sine of beta. Yes? Now, I could distribute this, right? Sine of alpha, cosine of beta, over cosine of alpha, sine of beta, plus cosine of alpha, sine of beta, over cosine of alpha, sine of beta. So this gives me a tangent times cotangent. So tangent of alpha, cotangent of beta, plus, oh, I guess, and then this gives me that becomes a 1. What would you want to do here? You got to separate those. I told you I was doing a problem I haven't done yet before. That's a good problem. Why don't we try to work on this side real quick? Oh, wait, no, that would be. Hold on real quick. Oh, this should be a cosine of beta, right? Now, what did I do wrong here before? I'm still not sure. Cosine of alpha plus sine of beta cosine of alpha all over cosine of beta cosine of alpha. And do you guys see that this is the sum and difference of two angles? It is. Did you follow that, Sarah? Because actually, I didn't figure it out on the first round, so I stopped. I worked at a different approach. But some people got very tired with that, and they didn't want to wait for it, so they just started talking and getting distracted, and then they missed the whole idea of saying, hey, usually the left side works, but then, I kind of got stuck working on the left side. So I stopped, erased, tried the right side. And guess what? The right side went ahead and worked perfectly fine. Because this is that formula, right? So I could rewrite it like that. You can just rearrange the sign from the front one. But it works, right? Now, we don't know what alpha and beta. These are variables. But again, we want them to look like the left-hand side. So I am going to just apply the formulas with theta and beta. So we have sine of alpha cosine of beta plus cosine of alpha sine of beta. And then here is like my plus. So this was that one, right? And then now I'm going to do this one. So this is sine of alpha cosine of beta minus cosine of alpha sine of beta. So that is that one. So I basically did the sum and difference formula for both of my expressions, right? And now I just want to look for like terms or terms that cancel out. Well, you can see that these two terms are going to add to 0.
these two terms are exactly the same. And there you go. So again, as we discussed, guys, there's many different ways. We could do 45 minus 60, 30 minus 45, negative 60 plus 45, negative 45 plus 30. And again, there's not one right way or not. And typically, I will let you guys know, I'm not going to ask you guys to break these up. Typically, I will give them to you already broken up. You just need to be able to apply the formula. So I'm writing this as 30 degrees minus 45 degrees. OK? So we can see that we have the sine of the difference of two angles, right? We know from radicals, which I erased, I apologize for that, but that does not equal the sine of 30 degrees, minus the sine of 45 degrees, right? We just discussed this with the radicals, yes? So don't do that. Even how frustrated and stressed out you can be on your test, don't resort to that. We have a formula for it. And the formula is based on our two angles, at least u and v. So what I'm going to do is I'm just going to label these u and v. All right, and for the first one, I'll just do this very elementary. And then from now on, after this, we'll just kind of, we'll skip this step. But remember, guys, the sum and difference of two angles for u minus v is sine of u times cosine of, is it u? I forget. No, it's sine of u times cosine of v. It's been a while. It's been a year. And then that's going to be minus the sine of v times cosine of u, right? Now cosine of u times sine of v. OK, well, either way. Doesn't really matter for those two. Make sure you get a good tail on your u so you don't mix it up with your v. All right, so now, guys, I have my u and I have my v. Now I'm just going to substitute everything in. Again, you don't need to show this step. I'm just doing it so you guys can kind of see. But I mean, we're just going to do sine of 30 degrees times the cosine of 45 degrees. Now, be careful, guys. Again, it's u minus v. Like, think of these as like in parentheses. So v is not negative. It's u minus v, so you use that formula, right? Yes? Yes. So just be very careful with that. So that's cosine of 45 degrees minus cosine of 30 degrees times the sine of 45 degrees. Yes?
What if it's not, what if you can't use that to get to 15?
What do you mean?
What if it's like 67?
That's going to be something we'll talk about later. But for right now, everything is going to be used from there, for at least today's lesson. OK? So now we just got to evaluate. And look at, remember when I first introduced the unit circle? I said like doing the unit circle problems is like just one little step, right? Yeah. So I mean, you guys can see we're doing 4 of these problems. Now, obviously, there are only 2 angles, so there shouldn't be that difficult. But sine of 30 degrees, so I just got to think 30 degrees. 30 degrees, that's going to be 1/2. Cosine of 45 degrees is square root of 2 over 2. Cosine of negative or minus cosine of 30 degrees, which is going to be a square root of 3 over 2. And sine of 45 degrees is a square root of 2 over 2. All right, so here comes in the multiple ways. Now, once you guys get to this point, you're basically, it's just asking you to simplify, right? I mean, because this is it, done. Like, really, this is like good. You did it, OK? Now we got to prepare ourselves for the multiple choice type questions, right? So one way you might see a multiple choice question is factoring out the square root of 2. Do you guys see how they both share a square root of 2? So some multiple choice might factor out the square root of 2. And that would be left with a 1/2 minus the square root of 3 over 2. Okay. Some might actually multiply this straight through. So you have square root of 2 over 4 minus the square root of 6 over 4, which obviously, if they have the same denominators, we could just rewrite this as, this would probably be written as square root of 2 minus the square root of 6 over 4. And then some might even just rewrite the 1/4. Or take out a 1/4 and have this as the square root of 2 minus the square root of 6. Like there's all these different variations, okay? My main goal when I'm checking this is that you guys can at least get to this point, all right? And my preferred method I'm OK with you guys doing is at least seeing it from this point. But again, when I'm checking your answer, I'm looking for this, okay? Unless I ask you to simplify or in a position point. But I'm going to basically allow a lot of my simplifying to be done on the multiple choice questions. Okay, but do you guys see, I mean, really from here to here to here. Like that's really like our steps for these problems. Okay? Let's go and take a look at this one. Guys, again, I just want to let you guys know that I will provide you with the addition or subtraction. So in this one, we have cosine of 60 degrees plus 45 degrees. You will be provided the addition. You're not going to have to come up with that on your own. However, your homework doesn't. So it just kind of makes you think about that. So be aware. And again, at the end of the year, you might have to do something like that as well. So, but at least for my tests and quizzes, that will be provided. So then, using the formula for cosine, I'll say this is my u and that's my v. So using the formula, I have cosine of 60 degrees, cosine of 45 degrees, minus sine of 60 degrees times the sine of 45 degrees. Okay, that's based on the formula that's on your sheet. Now I just need to evaluate. I erased my unit circle, which I shouldn't have done, because this is where a lot of people make mistakes because they want to do everything in their head. So just make sure you guys are very careful with this. Cosine of 60 degrees, imagine 60 degrees, cosine, okay, that's 1/2. Cosine of 45 degrees, that's going to be square root of 2 over 2, minus the sine of 60 degrees is going to be square root of 3 over 2. Sine of 45 degrees is the square root of 2 over 2. Now we just multiply and simplify.
Okay, so for this type of angle, these get a little bit difficult because now what we got to do is we got to determine how am I going to split up tangent of 17 pi over 12 into two different angles that I can use to find the values on the unit circle. So a lot of this kind of comes into play. One thing you got to remember is, all the points that we know on our unit circle can either be broken up into multiples of pi over 6, pi over 4, pi over 3, and pi over 2. So what I did is I just kind of worked in, thought of a couple problems and just pretty much picked some numbers as far as for my numerator that I can work with, either adding or subtracting, to get me at 17 pi over 12. And what I came up with is I can rewrite 17 pi over 12 as tangent of 9 pi over 4 minus 5 pi over 6. So when I get these to be the the common denominators and I subtract, I end up getting 17 pi divided by 12. So now the next thing I need to do is use our formula. So the tangent of two angles subtracted from one another equals the tangent of u minus the tangent of v divided by 1 plus the tangent of u times the tangent of v. So to plug these in, I'm going to represent 9 pi over 4 is my u, and negative 5 pi over 6 is my v. So now to complete this, what I simply need to do is find the values for u and v. So all I need to do is determine where on my unit circle is 9 pi over 4. Well, remember, we can break this down. 1 pi, 2 pi, 3 pi, 4 pi, 5 pi, 6 pi, 7 pi, 8 pi, 9 pi, right? So, or you can just always think about it as, 2 pi over 4. So this coordinate right here is radical 2 over 2, comma, radical 2 over 2. Paul, are you getting this, or what's up? No? Too much? I already lost you?
No.
Too much? Okay. So the next one I need to determine is where is my point 5 pi over 6. Don't think of it as the negative. Remember, we're subtracting our two angles. So I still need to find 5 pi over 6. Well, If I was to break this up into thirds, we'd represent that, or into 6, we'd know that 5 pi over 6 is going to be this angle right here, which is negative radical 3 over 2, comma 1/2. So let's see here. The tangent of, now I got to plug in my u and my v. So let's go and get to this. So now I'll plug in my u and my v. So tangent of 9 pi over 4 minus 5 pi over 6 equals tangent of 9 pi over 4 minus tangent of 5 pi over 6 divided by 1 plus tangent 9 pi over 4 times tangent of 5 pi over 6. Now, if you've done enough of these trig problems, you would notice that the tangent of pi over 6 or 5 pi over 6 is going to produce you either a positive or negative with a radical 3 over 3. But let me just show you just in case you forgot. So remember, tangent is y over x. Well, here, my 2's will cancel out, so I'm left with 1/2, or I'm sorry, 1 over radical 3, rationalize the denominator, and my final answer is radical 3 over 3. And sorry, that's a negative, right? Over here, my y over my x, that's the same, this exact same number on top, so my answer is going to be equal 1. So the tangent of 9 pi over 4 is going to equal 1 minus tangent of 5 pi over 6 is going to be a negative radical 3 over 3. Divided by 1 plus tangent of 9 pi over 4, which is a 1. And times the tangent of negative 5 pi over 6 is a negative radical 3 over 3. So the one thing I always like to ask my students is when they get mixed up, they get to here and they're like, holy crap, what do I do next? Well, if you remember when we were solving fractions with equations with fractions in them, the first thing that you were told to do when you had a problem like this and I said, hey, solve for x, first thing we did was multiply by 4 to get rid of that denominator 4. It's the exact same thing here. We want to get rid of our denominators of 3. So what I'm going to do is I'm going to multiply the top and the bottom by 3. And you got to make sure you multiply everything times 3. Now, first of all, a couple things we can notice. Here I have a double negative. That can turn to a positive. All right? And this wholly is going to fully turn into negative. So when I multiply my 3 times everything, I get 3 times 1, which is equal to 3. 3 times radical 3 over 3, which is equal to a positive radical 3. All over. 3 times 3, which is 3. And these cancel out to a negative radical 3. Again, almost like everybody's like, oh, I'm done, right? Well, be careful, not yet. We still are trying to divide by an irrational number, which we cannot do. So now our next piece of work is now we have to rationalize the denominator. I know, it's getting a little long. So I multiply 3 plus radical 3 on the bottom, 3 plus radical 3 on the top. Here, I have a difference of 2 squares. So I know my answer is going to be 9 minus 3, which obviously we can reduce down to 6. Here, I have a perfect square, so that's going to be 9 plus 6 radical 3 plus 3. Let's get this work out of the way. So now when I go and combine these, or plus 3, geez. So now I combine these, what I get is 12 plus 6 radical 3 over 6, cancel, cancel, cancel. What I end up with is 2 plus
Sarah Holiday, please report to the front office.
And that's
Sarah
it.
Holiday, please report.
Right. But the problem with this is 15 degrees a cross at a coordinate point on the unit circle that you are familiar with? No. So if I asked you to evaluate on a test, the first inclination would not be to use your unit circle, but would be to grab out your calculator, right? And however, the problem with the calculator is it's going to give you approximate value. It's going to give you a decimal, and then you're going to have to round it. And if that's what happens on a test, and they say, hey, round to the nearest hundredth, then yeah, plug in your calculator and round to the nearest hundredth. However, there's another way that we ask is, in our text, we ask for the exact value. So to find the exact value, we're going to use the formulas. So there's only, if you guys remember in the unit circle, there's only so many angles we have, right? We have 30,
45, 60, and 90. Right? And you guys could do radians as well. So what I want to do, if you guys look at those, these are called the sum and difference angles. You can only do the sum and difference angles. You can only find the exact. You can use these formulas. Well, you can use these formulas for anything. But to find these exact value that we're going to be doing in this class, you're only going to be able to do that for angles, for the sum and difference of the angles that we know on the unit circle. If not, you'd be approximating as well, and it'd just be faster to use your calculator. So can I rewrite 15 degrees as the sum or difference of any of these two angles that we do know? Yep, you could do what? 45 and 30. So I could rewrite this as sine of 45 degrees minus 30 degrees. Would you guys agree with me?
Yes.
OK. So that is a difference of two angles. OK? So if you guys look at that, you can see my variables I use is u and v. Here is u. Here is v. So the way that works is it looks like this. Just, no, it doesn't really matter. So the sine formula for sine of u plus v, so it's not plus or minus, but when you do plus, then you do the top sign. So it's plus and plus. If you guys look at cosine, you do plus and then minus, or minus and then plus. Does that make sense?
Wait,
So
yeah.
for the sine formula, it's u plus or minus v. So if it's u plus v, then with the formula, you're going to do the top sign as well, plus and plus. See how cosine, it goes, see?
Okay.
You either do plus minus or minus plus. Plus plus, minus minus. Plus plus, minus, minus minus plus. So it depends on what the formula is. So we have sine of u minus v equals, what do I have? Sine of u times the cosine of v plus cosine of u. No, wait, this is minus, right? Minus, minus. Minus cosine of u times the sine of v. That's the formula. That's given to you. The hardest part is, one, finding the formula that it's given to, and then two would be to using the algebra, which we'll get to next. So now we've identified u, we've identified v. All we do is plug them in. Ooh, this is like algebra 1 again. Yeah.
If I could remember that, I would.
I do not remember baffling algebra 1.
Well, because I don't like it.
Algebra 1 was the last year I loved math.
OK. So if you guys go ahead and take a look at this, now it's kind of like what we just did, what I'm asking you guys to do in your quiz next class period, overload. Now you have what? You have like 4 of them. Fortunately for us, though, by writing this down, you guys can see that these are all in the first quadrant, right? So it's really not that bad. So the sine of 45 degrees, that's going to be square root of 2 over 2. The cosine of 30 degrees is going to be square root of 3 over 2. I'm just doing these in my head. If you guys want to verify using the unit circle, please feel free. Oh, one thing I wanted you to notice. It says cosine of v. V is 30, not negative 30. OK? Because it's u minus v, right? That's the formula, u minus v. You're plugging in v, not negative v. Does that make sense? Well, that's a common mistake. Cosine of 45 is square root of 2 over 2. And cosine of 30 degrees is 1/2. Does everybody follow me with that? That's not it, though, not yet. Well, we got to simplify. Just got to square root of 2 times square root of 3. We're learning this in our Algebra 2 class. That's square root of 6 over 4 minus the square root of 2 over 4. OK? Now, that's how the way that the book writes the answer. Actually, they write their answer like this. They write their answer like this. Square root of 6 minus 2 over 4. Which is fine. OK? I want to present you guys with all the other ways. The old book that we used to use used to factor out a common term. What radical could we factor out that they have in common? Square root of what number do these 6 and 2 share? 2. So the old book, factored out a square root of 2 and left the answer like this. So they factored out a square root of 2 over 4 and left it like that. I don't know what the answer on the end of the course exam might be, but just realize these are all equivalent to each other. I really don't care which way you guys have it simplified. I think all 3 of these will be fine for me.
That one, why is it the square root only over 6 and not over 6?
Oh, I'm sorry. Sorry.
Yeah, that was my question.
All right, welcome. What I'd like to do is show you how to solve this equation here. And the important thing you notice is we have a cosine of 2x and also cosine of x. So when solving a problem like this, what I'm going to have to use is use my double angle formula. So I notice I have cosine of 2x, so what I did was I previously wrote up my double angle formulas for cosine. And you can really use either one that any one that really kind of suits you the best. And so I'm going to kind of determine which one is going to work. Now, obviously, for if you have the sine, double angle sine, there's only one formula that we've been provided, so that's what you're going to have to use. But for cosine, we can pick and choose which one we want to solve for. So, and I'm looking up here. Remember, when we're trying to solve for an equation, we want to get that variable, isolated, right? Or we need to write it as a sum of two products that equal 0. So when I look up here to solve this problem, I can't isolate just one cosine. I have two separate cosines in here with my variable x. So I can't combine these any further. And I can't right now, I can't right now factor out a cosine that's going to give me the product of two cosines that I could use. So I need to get rid of this cosine of 2x. So what I'm going to do is I'm going to pick a problem. Now if I choose this first formula, I'm going to introduce sine. Well, I don't really want to introduce a sine and a cosine. And here, if I introduce this formula, I'm going to be, again, introducing a sine. So what I'm going to do is, rather than write cosine of 2x, what I'm simply going to do is I'm going to now rewrite that as 2 cosine squared of x minus 1 minus cosine of x equals 0. So all I've done is I've replaced the cosine, the double angle cosine, with the formula 2 cosine squared of x minus 1. And again, the x and the u, those are just your variable for your angle, or your unknown angle. So now what I'm going to do is I'm going to rewrite this in kind of a standard form. And what I'll notice is this follows a very resemblance of a trinomial that I can factor. If I kind of forget about my trig functions right now, and I just rewrite it as 2x squared minus x minus 1 equals 0, what I want to do is I want to say, well, can I factor that, right? I mean, that's a trinomial. Let's see if we can factor this. And what I'll notice is since my middle term is going to be negative, I'm going to want to subtract, I'm going to want to multiply my 2 times a negative 1 plus 1. And then so what I notice is that factorable? Does that work? Yeah, it does. So what I can do is I can rewrite this as 2 cosine of x plus 1 times cosine of x minus 1 equals 0. So now what I've done is, rather than isolate one of them by themselves, I've been able to create a product that equals 0. And we know when we have a product that equals 0, we can rewrite these both to equal, one of these has to equal 0, so we can rewrite them as 2 cosine of x plus 1 equals 0, or cosine of x minus 1 equals 0. Now I can simply solve. And I get cosine of x equals negative 1/2. And here I add a 1 to the other side, and I get cosine of x equals positive 1. Now I need to take a look at my unit circle, and I believe I forgot to write in what the constraints. I believe the constraints of this problem are between 0 and 2 pi. So we're not going to be adding any simple answers here. So first of all, when does cosine equal 1? Remember, cosine is our x value. Well, if you look at our first point, that's going to be 1, 0. The angle at that point, since it is included with 0, is going to be x equals 0. So that's going to be our angle when cosine of x equals 1. Now over here we have negative 1/2. Well, negative 1/2 is going to be that angle down there and that angle right there. And I can write that as negative 1/2 radical 3 over 2. And this one's negative 1/2, I'm sorry, that's positive, yep, negative radical 3 over 2. So those two angles, where I have those points, are going to be, x is going to equal, let's see, 2 pi over 3 and 4 pi over 3. And ladies and gentlemen, that is how you solve when you have to do factoring. Factoring to solve your with the double angle formula as well. A lot of stuff, right? There you go. Then what we did is we solved for the angle, right? So we had solved for our tangent and cotangent, and then once it was 2x, then you divide out the 2 and solve for your x. Now, we have a problem with this equation because I need to solve for tangent of x. Now, there's two different ways that we learn to solve, Hannah. The first way that we learned to solve was just using inverse operations, right? You're just undoing what's happening to your function, get it isolated, and then evaluate. Or the other part was if you couldn't just use inverse operations, we worked on factoring, right? And you just go ahead and factor them together, and then you can use the zero product property to solve. Well, we have a little problem here because if you guys look at this, I can't really do a factoring. I can't factor something out. I mean, there is a couple, factoring part, but it's going to be a little bit difficult as far as working on factoring, and I can't just isolate it if I have two different functions with my variable. So what I'm going to apply is I do notice that I have a double angle. So I can apply the double angle formula. So that's what we're going to insert. So I'm now going to say, rather than tan of 2x, I'm going to say 2 tan of x over 1 minus tan squared of x minus cotangent of x equals 0. Okay?
Why did you replace that?
Well, because now I can replace it. So now what this is just going to be working with, now I can either try to work on maybe trying to isolate something or maybe work on factoring in a bit.
So the TU can stand for TX?
Yeah, this is just the general formula. Yeah, so U is representing your angle, but in the problem we're using x. So, all right, so now let's just kind of do some math stuff. See if I can get it somewhere where I can solve for x. So let's add the cotangent to the other side. Therefore, I have 2 tangent of x divided by 1 minus tan squared of x equals cotangent of x. All right, and the reason why I wanted to multiply that or add that to the other side is I want to get this 1 minus tangent squared off to the other side. All right, I want to get this off the denominator. So I'll multiply both sides by that. All right, so we know this is going to divide out to 1, leave me with 2 tangent of x equals, now if I apply distributive property here, I'm going to have the cotangent of x minus tangent of x. Okay, notice how cotangent times tangent, tangent squared, one of the cotangents times tangents will go to 1, just leaving you with one more tangent of x. Follow me with that? Okay. Yes? Okay. So now let's go ahead and get all of them on the same side. So you guys kind of notice how now we're looking pretty similar. Now we got rid of that square. That's nice. So let's add the tangent. And let's subtract the cotangent of x. So if I add the tangent and I subtract the cotangent of x, I'm now left with 3 tangent of x minus cotangent of x equals 0. Whew. Okay, well I don't have a multiple angle, so I can now at least try to combine these. So to combine them, I can rewrite this as if this is. I could rewrite this as 1 over tangent of x over 1. So therefore, to get them to be the common denominators, you can multiply by tangent of x over tangent of x. Therefore, I'll have 3 tangent squared of x minus 1 over tan of x equals 0. Yes, your question. Okay. Notice I have 3 tangent of x over 1 minus, I converted the cotangent to 1 over tangent of x. Because I want to combine these two.
I didn't know if the tangent over tangent was, but no.
Yeah, so that's why. So what I did is I multiplied because right now I have an equation. I had an equation 3 tangent of x minus cotangent of x equals 0. Well, what are you going to do for this? We still need to solve, right? And if you guys remember when we did our section on solving, you need to do something. You either isolate, you either factor, or you do something. Well, I can combine like terms. I can combine a tangent and cotangent. I just need to make sure they have the common denominator. So over here, my denominator is tangent. Over here, my denominator would be 1. So I get common denominators. And now I have something, 3 tangent squared of x minus 1 equals 0. Well, the tangent's not, well, I could divide it into both of those. But the way I'm going to rewrite it is cotangent of x times 3 tangent squared of x minus 1 equals 0. What's cotangent? 1 over tangent, right? So if you multiplied 1 over tangent times this, it would give you, if you multiplied 1 over tangent times this, then it'd be cotangent. All I did was I just rewrote. Dividing by tangent is the same thing as multiplying by cotangent, right? Right? If you take dividing by 2 is the same thing as multiplying by 1/2. Now, why would I do that, or why would I not think about it? Why would I not do what you asked and just say, why don't you just divide it into both of those? I can divide it into both of those. If I divide it into both of those, then I'm going to go back and I'm going to get an answer, go back to where I was, right? If you divide the tangent back into both of them, you go back to this answer again. You go back to 3 tangent divided by 1 and 1 divided by tangent, right? So I don't want to go back dividing by 1. Remember, ladies and gentlemen, there's 2 things we looked at: solving or isolating the value, or zero product property. So what I'm doing is I'm writing my division as a multiplication. Why do I want to write it as a multiplication? Because now I can say the cotangent of x equals 0, or 3 tangent squared of x minus 1 equals 0. Now we can solve for these, right? Because now I wrote a multiplication problem that sets me equal to 0. So you say cotangent, when is cotangent equal to 0? Right? And we're going to find all of our solutions. So remember, cotangent of theta equals your x over your y.
Sorry, where are we?
I have this. Okay. This is a zero product property. If this times this equals 0, that means cotangent equals 0, or 3 tangent squared minus 1 equals 0. So now I'm solving each one. So now I need to look at, when does my y over x equal 0? It is x over y. So when does my x over my y equal 0? Right, so you could say x equals pi over 2. And then if you notice, though, x equals pi over 2 and x equals 3 pi over 2, those are only a pi difference away from each other, right? So I could say x plus pi n. That's for those solutions, because we're finding all the solutions. Then here, I'm going to want to add 1. So I have 3 tangent squared equals 1. Divide by 3. Tangent squared equals 1 over 3. Take the square root. Tangent of x equals plus or minus 1 over square root of 3. Rationalize the denominator, equals plus or minus square root of 3 over 3. And what problem was this again? 15? So what do I have? I have the right plus or minus square root of 3 over 3. Oh, yeah. OK, so now I need to look at this and say, when does the tangent equal the square root of 3 over 3? Well, if you look at our first coordinate point, which is square root of 3 over 2, comma 1/2, the tangent of that value, the tangent of this angle, which is pi over 6, equals y over square root of 3 over 2. Rationalize the denominator, equals square root of 3 over 3. So it's going to equal, remember we're doing the plus or minus, so you're going to have pi over 6, 5 pi over 6, 7 pi over 6, which is which will be the other positive, 7 pi over 6, and then 11 pi over 6. So your angles, final answers here, are going to be x equals pi over 6. And remember, all you need to do is add pi to get to the other positive answer, which would be pi n. And then x equals 5 pi over 6 plus pi n to give you the other solution. Right? Because remember, we don't need to write in all 4 solutions. We're trying to find all the solutions. So if you write 5 pi or pi over 6 and you add pi to it, that's going to give you the other positive solution. And if you keep on adding pi, you're going to get all the solutions. Same thing with 5 pi over 6 takes me to 11 pi over 6. You can just keep on adding them. So the solutions we have there, and then your cotangent solutions are going to be right there. Whew. OK. So we look at an equation here, and I have 2 cosine of x plus the sine of 2x. And looking at this, trying to solve, what we did usually before when we had 2 different functions was we were able to somehow get multiplication involved where we could solve for x or y, right? Or we could solve for either the sine or the cosine. So when we have 2 different functions, we can't isolate one and just kind of forget about the other. But a lot of times we need to somehow get multiplication involved so we could apply the zero product property. And this one's kind of getting a little tough because I'm not seeing any multiplication. The only thing I can do is just add one to the other side, but that's not going to help me solve. However, we do have a double angle. And what we're going to be working on today is actually applying using the double angle formulas. So what I'm going to do is I'm going to rewrite sine of 2x for the double angle formula. So now I can write 2 cosine of x plus the sine of 2x. Let's go and write this over here. Here. The sine of 2x equals 2 sine of x cosine of x. So that's the double angle formula that I'm going to use. So now I'm just rewrite sine of 2x. Rather than writing it like that, I'm now going to write it as 2 sine of x cosine of x equals 0. So all I'm really doing is taking a formula and then applying it to my equation, because now I look at this and I say, all right, by looking at this equation, now I can factor out a 2 cosine of x. And that's going to leave me with a 1 plus sine of x. I factored out a 2 out of both of them.
Yeah, but there's also 2 sines.
No, this is 2 times sine times cosine. So there's 2 of that whole, it's 2 multiplied by that whole product. So I'm factoring that 2 out from there and from there. Does that kind of make sense there? So now, since I factored out, now I have a product that's going to equal 0. Now I can apply the zero product property. Okay, so we're working on trying to find all the solutions to this problem. So I have cosine of 0, so I'm going to go back on the interval of 0 and 2 pi and determine when is cosine of x going to equal 0. Well, on the 0, 2 pi, I have this at angle at pi halves. I have the coordinate point 0, 1. And at the angle of 3 pi halves, I have the coordinate point of 0, -1. Hello, Mr. Massey.
I have this to go later.
OK. I'll go and give it to him. Thank you very much. So I have cosine of x equals 0, and then sine of x equals -1. And now we need to look at when sine of x equals -1, which we notice is going to be at 3 pi over 2. So I could say x is equal to pi halves, and x is equal to 3 pi halves. And then to incorporate all the solutions, we notice that these are pi difference away from each other. So I'm not going to worry about writing the solution. I'm just going to have x equals pi halves plus pi n. And since that's going to be the same solution for when sine of x equals -1, I'll be able to keep the same solution. OK? Pi halves. So this is when x equals pi divided by 2 plus pi n will satisfy both your equations. Okay? All right. First of all, I just told you on the last problem, if you see the double angle, look to use the double angle formula. So a lot of you guys would look at this one and say, well, OK, let's use the double angle formula. But the problem is, now what are you going to do? You can't apply the zero product property because you don't have anything equal to 0, right? And if you add it to the other side to get 0, then you don't have a product anymore. So if we apply the double angle formula, we kind of take us to a dead end at this point, at least for what we've learned. So this is not actually going to be helping us. And if you remember, what we did is that when we first learned about solving with double angles, we talked about, or multi-angles, we talked about, well, we can, if there's only a term isolated, if we have one term isolated, we can just solve this as is, right?
Yes.
We can just solve this for 2x. And what I did is sometimes I said, you could use substitution if you want to. Let 2x equal theta. Let's just do that. So then I'm just going to rewrite the problem as sine of theta equals -1/2. Now again, we don't want to forget this, all right? But now I'm just going to use this to solve. So I say sine of theta equals -1/2. Well, I got to figure out when is sine negative. So remember, sine is the y-coordinate. -1/2 has, if you remember, this coordinate point is square root of 3 over 2, comma 1/2. So that's when the y-coordinate is 1/2. But we need to be at negative, so it needs to be down here. Same reference angle as pi over 6. So that means the angle needs to be, huh? Sine is y. Sine is the y-coordinate, right? Yes. So theta equals 7 pi over 6. However, there is an important thing there. There is no restrictions on the domain. It says the general solution. That means all the remaining solutions. So if I have 7 pi over 6, how many times can I keep on getting this as a solution? Infinite many times. Now, I don't want you to confuse this angle right there, because this is your solution. And to get back to the solution, I have to add 2 pi. And how many times can I add or subtract 2 pi? Infinite many times. So we use a variable n to represent that. Then we have our other angle here, which would be 11 pi over 6. So theta equals 11 pi over 6 plus 2 pi n. However, our example, we're not solving for theta, guys. We're solving for x. So we can write this as 2x is equal to 7 pi over 6 plus 2 pi n. And 2x is equal to 11 pi over 6 plus 2 pi n. Now, to solve for x, divide by 2 on both sides. And I get x is equal to 7 pi over 12 plus pi n. And x equals 11 pi over 12 plus pi n. So does anybody have any questions on where the pi n or 2 pi n came from, or the answers, the 7 pi over 6 and 11 pi over 6? Or just any questions in general? When we're looking at this, guys, I automatically see it's not on the unit circle. So I know I have to create a triangle. I just need to go ahead and determine where is this on the unit circle. All right, well, I know if this is pi halves. That's the wrong one for the wrong problem. She's not here right now today. Yeah.
Yeah, pi less than 2, less than 3.
Oh, OK. OK, right? All right, so still we have to do the same thing. Here's our problem. We don't have the so if we know that this is pi halves, that's pi, that's 3 pi over 2. So therefore, our angle has to be in the third quadrant. So I draw an angle in the third quadrant, right? And remember, all of our triangles have to be exactly the same, where we have this perpendicular side. And then our center angle, our angle has to be a central angle, u. So we're given cosecant, right? Remember, cosecant is hypotenuse over opposite. Well, our hypotenuse is never going to be negative, so that's going to be 5. That's -3. And that makes sense, right? The 3 would be negative because the sign is down. So now we need to determine this. Hopefully you guys know this is a Pythagorean triple. So it has to be 4. But since it's in the third quadrant, it has to be a -4. Okay, so now what I'm going to do is to show you guys how to find the sine of our half angle. So if we're trying to do sine of u over 2, well, using that formula, that's going to be plus or minus the square root of 1 minus cosine of u divided by 2. Now, here's where I didn't have time to get into this, but I want to make sure you go. This angle for sine, right, is positive or negative? Is it positive or negative for sine? Negative. So therefore, instead of doing plus or minus, we're just going to be talking about the negative square root of it. All right? For cosine, when we do cosine, is it positive or negative for cosine? Negative. So it would be a negative square root. Okay? So it's not always plus or minus. It depends on where the angle is. If the angle's in the first and second quadrant, then sine would be positive. If it's in the third and the fourth, the sine would be negative. All right? So now we just need to evaluate what cosine of u is. Well, cosine of u is going to be adjacent over hypotenuse, right? So therefore, we have negative 1 minus a negative 4 over 5. Okay? Don't forget that cosine of u is negative 4 over 5, and it's minus a negative. And then that's over 2. So I can rewrite that as 1 plus 4 over 5 divided by 2. And again, we don't like 5 in the denominator, right? So we do the same thing over and over until you get really sick of doing these problems. You multiply by 5 over 5. Make sure you distribute. So therefore, you obtain 5 minus 4 all over 10. I don't know why minus. It's positive. Yeah, it's positive. Yeah, I don't know where negative came from. So now you add them. So now I'll simplify this over here. So it's negative the square root of 9 over 10. I'm not going to break up this fraction because I did that last time. But you guys can see that now I can simplify the numerator. So it's negative square root of 3 over 10. Right? And then I rationalize the denominator. And I get negative 3 square root of 10 over 10. And there you go. All right, so we have this sine of 2 theta equals sine of theta. Now, again, I wanted you guys to try some things, like play around with this. Like, what can you do? And the best thing I look at this is I have two functions, right? And if you guys remember from Algebra 1 and Algebra 2, whenever you had two functions that were on either side of the equation, we usually wanted to get them to the same side, correct? So why don't we just get these to the same side? So we have sine of 2 theta minus the sine of theta equals 0. Now, typically, we'd like to combine these. But we recognize these are not the same function or the same angle. Like they're not, we can't combine them. It's kind of like square root of 2x minus the square root of x. They don't have the same radicand, so you can't combine them, right? So, what do we do? Like here, we could obviously, look into this equation might be actually using the square root or using the inverse operation. But inverse operation isn't really going to help us here with the thetas. Because if you guys remember, when we previously talked about getting rid of this 2 theta, we had to get rid of the sine function kind of first by evaluating this. So we're kind of stuck. But now, if you guys kind of look on the board, you guys can see we have some new formulas where we can actually represent sine of 2 theta using what we call the double angle formula. So that sine of 2 theta is 2 sine of theta cosine of theta minus the sine of theta equals 0. So we can rewrite the sine of 2 theta using this formula that we are now provided. Now, this gives us some options that we are more familiar with, right? Because now we have an equation that, to solve this, we can just factor out a sine of theta. By factoring out a sine of theta, we have cosine of theta minus 1 equals 0. Now we can apply the zero product property. And therefore, cosine of theta equals positive 1/2. OK, so if you don't know the unit circle, you're going to be quickly start getting left behind here. So the sine of theta is equal to 0 at what angles? Think about the unit circle. That's 0 and pi.
the cosine of theta is equal to 1/2. That is going to be at, let's see, 1/2. So that's going to be pi over 3 as well as 5 pi over 3. And because I did ask you to find the answers between 0 and 2 pi. So that would be your solution set. I just want to go through this again, though, just to remind you guys, because number 5 through 10, you guys are given these double angles. So I want you to apply the double angle formula. So therefore, this is 2 sine of x cosine of x equals sine of x. Then what I started off in last class period, yes? Equals 2 sine of x. Thank you. Wait, so that was it? Really? OK, yeah, you're right. All right. So, and then I used my double angle formula, which is 2 sine cosine. Now, to solve this, I got to get these to the same side. So therefore, I have 2 sine of x cosine of x minus 2 sine of x equals 0. Can you please put that away? Now, the next thing that I can do, you guys can see, is they both share a sine of x, or 2 sine of x. So I can factor out a 2 sine of x. By doing that, I get cosine of x minus 1 equals 0. Now, what I can do is apply the zero product property. So you could say 2 sine of x equals 0, and cosine of x minus 1 equals 0. Were they asking you to find all the answers between 0 and 2 pi, I believe? So to solve for sine of x, I get sine of x equals 0. And then over here, I get cosine of x equals 1. So basically what they're asking is between the values of 0 and 2 pi, when is sine of x equal to 0 and cosine of x equal to -1? Well, if you look at your unit circle, cosine of equal to 1. Cosine is only going to be equal to 1 here, right? Because over here it's -1. And for these two angles, it's 0. And when is sine of x equal to 0? Well, sine is equal to 0 here and here. So if your angles have to be between 0 and 2 pi, that means 0 is included, but 2 pi is not. So therefore, my answers is cosine is equal to 1 at 0 or the angle 2 pi. But so 0 is going to be only 1 included. And then cosine is 1 at 0. Sine is 0 at the angles 0 and pi. Well, we already have pi, or 0, so we're just going to include pi. And that's your answer. Done. All right. Let's go and take a look at this one. Now, again, the tough thing with this one, guys, is like we can see we have a cosine of 2x, right? And so which one do we choose, right? Now, again, there's multiple different ones you could choose. And again, it doesn't matter. Some of them are going to be a little bit easier than others. So for the sake of this one, what I would recommend, I'd usually always start with the cosine squared minus sine squared. Typically, that's going to be one that's going to be helpful. Also, between the other two, usually it's going to be helpful to choose. You want to keep usually the same like sines and cosines. Like, so for instance, like if I want the left side to look like the right side, it would make no sense for me to change the cosine of 2x into terms of sine, would it? Right? That doesn't make any sense. I want to keep everything in terms of sines and cosines. So what I'd want to do then is I wouldn't want to convert this to sine. So I'd either use the first two. Now, I'll do the first one, and we'll see what that one looks like. So that's going to be plus cosine squared of x minus sine squared of x. And what do you know? Done. Right? Now, let's try maybe the second identity. So the second identity would have been sine squared of x plus, let's change this into a, actually, no. Yes. Yeah, that's right.
Wait,
What? Who?
which identity?
Actually, the sine squared actually is the one. Yeah, that's the one I want, actually. I spoke wrong. That's actually, I'd want this actually, a 1 minus a 2. Yeah, this one actually works. Why does this one? Yes, question.
So, which identity did you change?
The first one, the cosine of 2x. It's right there. Cosine of 2x is cosine squared of x minus sine squared of x. No, it's 2 cosine squared of x minus 1, which is another option. Now, I'm doing this again. Oh, you're talking about what am I doing for the second round or the first one?
No, I messed up.
OK. So now, what if I change, instead of doing this, what if I change it to this? Well, now I can subtract the sine squared and the cosine squared to give me 1 minus sine squared of x. What does 1 minus sine squared of x equal? Cosine squared of x. OK? And then if you were to do the third one, that is the one where the math would be a little bit more difficult, actually, for that one. All right, so in this case, now what they're asking us to do is now we want to find the tangent of 2u. So first of all, we want to make sure we can determine. Now, we already see tangent, right? So we already actually see the tangent of u. So to evaluate for tangent u, we don't really need to care about the triangle. However, if we were going to create, do the sine and the cosine, we would want to make sure we know our triangle is going to be within our constraint between 0 and pi halves. So therefore, it's going to be in the first quadrant. And we'd already have 3 over 4, opposite over adjacent. And then we know that would be a positive 5, just in case for your guys' own benefit, because if I ask you to do cosine of 2u and sine of 2u. But for the tangent of 2u, we have a different formula. So on page 387, as I mentioned, what you guys are going to want to do for the tangent of 2u is 2 tangent of u over 1 minus tangent squared of u. OK? So now we already know tangent of u, right? They already gave it to us. So we don't need to figure out anything with the triangle. Now we just need to plug everything in. Well, tangent of u is 3 over 4. So we have 2 times 3 over 4 divided by 1 minus 3 over 4 squared. Right? So I can simplify this as to 6 over 4 over 1 minus 9 over 16. Yes? Right? Now, I want to combine these. OK? So to combine these, 1 minus 9 over 16, guys, 1 is you got to have common denominators. So you multiply by 16 over 16 on the left side. So you have 16 over 16 minus 9 over 16, which is now going to give us 7 over 16. Right? So now I'm just going to start doing my work to the right. So now I have 6 over 4 divided by 7 over 16.
Wait, what are you multiplying 16 by the 1?
Yeah. I multiply 16 over 16. Will, can we keep your knees on your desk, please? Thank you.
By 9 over 16 and by 1.
No, just over 1. And then now you can subtract them. 16 minus 9 is 7. Yes? No. Not done yet. So now what we need to do is multiply. How do we divide a fraction by another fraction? Multiply by the reciprocal. All right? I'll use pink again. So now I'll multiply by 16 over 7. 16 over 7. Well, guys, you know that 4 can divide into 16. Well, no, this goes to 1, right? That simplifies to 4. 6 times 4 equals 24 over 7. And that's your final answer. OK? It's just some algebra practice, guys. It's really knowing your triangle, finding the constraint, knowing the formula, which you will have, but then just doing algebra. I mean, that's really all it is. OK? Which quadrant does this tell us? Third. Right? Because here's pi. Here's 3 pi over 2. So our triangle has to look like here. So here's our theta. Now it says 4 over 3. Now what do we know about the opposite and the adjacent side of a triangle in the third quadrant? Yeah, they are 4 over 3, but more importantly, what sign are they? They're both to the left and down. Right? And again, what was that number one thing that students made mistakes on this quiz? They forgot the signs. They would draw the triangle, be all happy, do the Pythagorean theorem, but they wouldn't address the constraint
and which sides are going to be negative or which ones are positive. OK, so now we just need to apply the formula. So we have sine of 2 theta, which we know is 2 sine of theta cosine of theta. Well, guys, can we find the sine and the cosine of this triangle now? Yeah, this is not too bad. Sine of theta is opposite over adjacent, negative 4 over 5. Cosine is adjacent over opposite. So now you just multiply them out. So 2 times 4 is 8, or 2 times negative 4 is negative 8, times negative 3 is going to be a positive 24, or 25. Done. So let's go through it again. So now let's just go to cosine. Now we kind of got a little bit of an introduction. We'll try to go through this a little bit quicker. So we have the cosine of 3 pi over 8, the exact same thing. We can't evaluate this on the unit circle. We could try to see if we could use sum or difference formulas, but we don't really like using sum and difference formulas, and I don't really want to think of what two angles add up to give me 3 pi over 8 or subtract to give me 3 pi over 8. So why even bother doing it when I can use my half angle formula, which I'll have provided to me, which equals plus or minus the square root of now 1 plus cosine of u divided by 2. So it's a little bit similar, or it's very similar to the sine, except now it's just going to be plus cosine. All right? So we, again, go back through. Well, if this is 3 pi over 8, that means that's equal to u over 2. So you could say u over 2 equals 3 pi over 8 multiplied by 2. U equals, that's 2. U equals 6 pi over 8, which is 3 pi over 4. Right? So then really what we're doing is we're just going to plug that in. So we could say x equals plus or minus the square root of 1 plus the cosine of 3 pi over 4 divided by 2. Right? Because our u equals 3 pi over 4. So you plug 3 pi over 4 in for u. Do you guys see that? The big mistake students do is they plug 3 pi over 8 in for u. No, 3 pi over 8 is equal to u divided by 2. Well, yeah, so now we need to evaluate. So now it's asking us what's the cosine of 3 pi over 4, which is negative square root of 2 over 2. Also, looking at the unit circle, is we need to look at the cosine value. For our angle of 3 pi over 4, which we said is negative square root of 2 over 2, comma square root of 2 over 2, is the cosine value obviously positive or negative? Negative. So rather than dealing with the positive square root, we're now going to be working with the negative square root, or the negative times the square root. You can't take the square root of a negative number, but you can take the negative square root. So now let's go and plug in. We said that's negative 3 pi over 4. So that's negative square root of 1 minus square root of 2 over 2 divided by 2. You got to get rid of that 2 in the denominator of the numerator, right? So you got to multiply by 2 over 2. Okay, make sure you apply distributive property. So negative square root of 2 minus square root of 2 divided by 4. And again, we can take the square root of our denominator. So we're equal to negative 2 minus the square root of 2 all over 2. Okay? All right, so ladies and gentlemen, if I'm asking you, here's 15 degrees, and I want to be able to evaluate it, we talked about using the sum and difference, right? I could definitely use the difference for this, right? I could do like 60 degrees and then minus 45 degrees, right? So you could do a difference if I want to do sine cosine. But I might also ask you, hey, give me that example as far as using the half angle formulas. And what the half angle formula is saying, and let's do the cosine of, u divided by 2. So if I take my angle and divide it by 2, then that's going to equal the plus or minus 1, I forgot the 1 plus cosine of u. 1 plus cosine of u divided by 2. So if I want to evaluate for 15 degrees, please note this is my angle that has already been cut in half. I can't evaluate sine, cosine, and tangent for 15 degrees, right? So don't plug 15 degrees in for your u. This is u divided by 2. Okay? So therefore, if I can say cosine of 15 degrees, which is u divided by 2, is equal to plus or minus the square root of 1 plus cosine of 30 degrees divided by 2. Do you see when I evaluate, all I'm simply doing is just multiplying it by 2? Because that's the formula. If it's u, cosine of u divided by 2 equals cosine of u, right? So cosine of 15 degrees is 30. I'm just doubling it. All right? The biggest mistake is students will write 15 degrees in here. No. That's 15 degrees, which is u divided by 2, which equals double that angle. Yes?
So whatever angle we're given, we just divide it with u divided by 2 and not divided by 2.
Well, this is that angle divided by 2. So you just multiply it by 2, right, to get you back to the actual angle we can evaluate for. So now, let's just go ahead and evaluate this, cosine u by 2. So now let's just go and figure out where cosine equals 30 degrees. So cosine at 30 degrees we already did, which was what? 1 half, right? Cosine of 30. No, 30 degrees at 60 degrees. Cosine is going to be square root of 3 over 2, right? So therefore, we have plus or minus 1 plus the square root of 3 over 2 divided by 2. Now, again, guys, we have a fraction, right? Stupid, stupid fractions. We have to add 1 plus the square root of 3 over 2. So I can say 1 plus the square root of 3 over 2. Again, multiply. Actually, you know what? You don't need to add them up. Another thing you guys could do is just multiply everything by 2. If you multiply everything on the top, and if you're going to multiply on the top by 2, you have to multiply the bottom by 2, correct? OK. So if I multiply across by 2 over 2, what I now obtain is plus. You could do it that way too, but now what I obtain is going to be 2 plus the square root of 3 over 4. OK? And then remember, guys, if I say the square root of 16 over 9, that's equal to the square root of 16 over the square root of 9. OK? The radical distributes amongst division. So therefore, I can rewrite this. I can't take the square root of 2 plus 3. That's an expression broken up by addition or subtraction. You can't distribute. However, I can take the square root of 4, right? So my final answer would be equals plus or minus the square root of 2 plus the square root of 3 divided by 2. Or you could write that as times 1/2 too. But OK? When completing a problem like this, ladies and gentlemen, we have the half angle formula, which says sine of u divided by 2 is equal to plus or minus the square root of 1 minus sine of u, 1 minus cosine of u divided by 2. All right? And what we're going to simply do is now I want to find sine of 3 pi over 8. Now, some of you got very close. And when getting very close to this problem, if you don't want to write down this first step, you don't have to. But I found a lot of people that didn't even get to the first step. And really, the first step is one of the easiest parts we can do for this problem. So if you're really, really confused, you want to start with this. If I say sine of u divided by 2 is equal to this, and then I say, what is sine of 3 pi over 8? First thing we know is these two are in the same spots, right? These are equivalent to each other. So if you kind of got stuck on this problem, the first step you're always going to want to do is set your half angle equal to your other half angle. So you can say that u divided by 2 is equal to 3 pi over 8. OK, Rachel? All right. So now the next step is obviously we have to solve for u. Because why do we have to solve for u? Well, if you guys look into the formula, that's not asking us to find the cosine of u divided by 2, is it? It doesn't say u divided by 2. It says just tell me what the cosine of u is. So if we know u over 2, what is u? Well, to do that, we multiply by 2 on both sides. Those divide out to 1. This reduces down to over 4. So therefore, I say u equals 3 pi over 4. So now what I can do is I can plug 3 pi over 4 in for my u. So therefore, I write plus or minus the square root of 1 minus cosine of 3 pi over 4 divided by 2. Is everybody following with that? So now we say, all right, the cosine of an angle. Well, we've been practicing finding the cosines of angles since chapter 4. So what we do is we go to our unit circle, and we figure out where's the cosine of 3 pi over 4. Well, here's 1 pi over 4, 2 pi over 4, 3 pi over 4. And we know that 3 pi over 4 has a coordinate point of negative square root of 2 over 2, comma, square root of 2 over 2. Right? So therefore, you can say the cosine, which is dealing with your x coordinate, is going to be negative square root of 2 over 2. So let's go ahead and plug that in. So we have plus or minus the square root of 1 minus negative square root of 2 over 2 divided by 2. Is everybody kind of following me so far with what I've done? All right. Then the next thing is, notice our angle. Our angle is in the second quadrant. In the second quadrant, is the sign of an angle positive or negative? Is the sign of the angle positive or negative? It's positive. So instead of doing the plus or minus, we're only going to be working with the positive value. All right, so we're not going to include the negative value because we're only concerned about the positive value because our angle is in the second quadrant. All right, so now we look at this and we say, all right, now we need to simplify this. Well, we have a fraction in the numerator and then divided by a number. So we need to get rid of this fraction. To get rid of the fractions, we need to multiply by 2. Because 2 multiplied by 1, or square root of 2 over 2, the 2's are going to divide out to 1. But wherever you multiply in the numerator, you have to make sure you multiply in the denominator. And then notice you're multiplying not by a number like you are in the denominator, but here you're multiplying by a binomial. So you need to make sure you put the whole thing in parentheses and apply distributive property. So therefore, I now have positive square root of 2. Double negative turns now to a positive. Now the 2's are going to cancel out. We got to remember to also multiply that by 2. So it's going to be 2. And then you'll have plus the square root of 2 over 2 times 2 is 4. Let's bring this down a little bit farther. All right? Then we know that, or hopefully we know that, you can break up the square root into square root of 2 plus square root of 2 over the square root of 4. Right? You can break up a square root when using division to the top and to the bottom. Yes?
I thought when you multiplied the 2 on the denominator by the other 2, it got rid of it.
Huh? Well, you got to multiply by 2 over 2. If you just multiply one thing, if you when you're multiplying a fraction, you have to multiply the same you have to multiply the numerator and the denominator by the same number. Right? Because think of 2 fourths, that's equal to 1/2, right? So, but if you multiply by 2 over 2, that gives you 4 over 8. And are those equal to each other? Yeah, so you have to multiply by 2 over 2, right?
So you don't have to get the 2 off the bottom?
Down here?
Yeah.
No, not initially right now. No, because what's going to happen is we don't have to get it off the bottom. We just want to multiply by 2. I see what you're kind of getting at is getting this 2 off. But remember, if you're just going to multiply by one number 2, then that means you have to multiply by 2 on the other side of the equation, right? So what I'm doing is I'm just multiplying by 2 over 2 right now. And what that does, that reduces it to here, which now I can take the square root of 4, right? The square root of 4 is 2. So therefore, now my next point is going to be the square root of 2 plus square root of 2 over 2. And you could also break that up into 1/2 times the square root of 2 plus square root of 2. Okay? So that's how you worked your problem. Okay?
Is that it? Can you reduce any further?
You guys understand that we could use the sum and difference formulas, right? And obviously, based on your based on the directions of what we're looking for, you could use the sum and difference formulas to figure this one out, right? We might also ask you to use the half angle formulas or doubling formulas. And basically, the half angle formula, you can see this is obviously sine, right? So the sine is going to be plus or minus. So the formula is sine of u over 2 equals plus or minus the square root of 1 minus the cosine. I didn't write that. It should have been cosine of u. Sorry about that. I gotta write those. I'm sorry, I messed up. That's not you, it's 2. Sorry. I was wondering, I was like, that doesn't really make sense. All right, so we have this as the cosine of u equals to 2. Now, basically what we need to do in this example, ladies and gentlemen, is you guys can see we have plus or minus. The plus or minus is basically going to be determining it with sine or cos. So you guys can see for sine and cosine, we have plus or minus. Tangent, we do not have the plus or minus because we're not going to be dealing with the radicals in this case, or the square root in those 2 examples I gave you. Basically, what we want to do is identify, is sine going to be positive or negative for our original angle? All right? And if you guys look at this, for our half angle, sine of 15 degrees, sine that 15 degrees is going to be in which quadrant? First quadrant. And is that going to be positive? Is that going to be in the positive, right? OK. And even when you double that, that's going to be, so that's going to be positive. So we don't need to worry about that it's a negative. Now, in the next thing, pi over halves is equal to, so we could say pi over 2 is equal to 15 degrees. Would everybody agree with me? See how these are like, we don't need to use this. Do you guys agree with me? Pi halves is equal to 15 degrees.
Yeah.
Yes? Because, well, and actually what they're asking for this problem is they use u. So we want to make sure we solve for u. So if we have u over 2 equals 15 degrees, then u has to equal u equals 30 degrees. So now we simply just plug 30 degrees into this formula. So the cosine of 30 degrees, if you guys remember, you look at the unit circle, cosine of 30 degrees, that's going to be square root of 3 over 2. Right? Now, again, we got to get rid of the radical, or we got to get rid of the 2. So just like we did in your last example for you guys, we got to get rid of the 2, so I'm going to multiply by 2 over 2. When I do that, make sure you apply distributive property in the numerator. You obtain the square root of 2 minus the square root of 3 over 4. Then, if you apply the rules of radicals, which we're teaching right now in my Algebra 2 class, you know that you can break this up into the square root of the numerator over the square root of the denominator. And then can I take this, you can't break apart the square root across addition or subtraction, but you can take the square root of 4, right? So your final answer is the square root of 2 minus the square root of 3 all over 2. And that's it. That is the exact answer. OK? OK, for this problem, what we need to do is we need to evaluate for the cosine of 75 degrees. We're going to evaluate using the half angle formula. So the half angle formula says cosine u divided by 2 equals plus or minus the square root of 1 plus cosine of u all divided by 2. So if I know that the cosine of 75 degrees is u over 2, I need to figure out what u equals. To do that, I'm going to multiply by 2 on both sides, and I get 150 degrees equals u. So now what I can do is I can plug that in for, so cosine of 75 degrees equals plus or minus radical 1 plus cosine of 150 degrees all over 2. Now I need to determine what is the cosine of 150 degrees. So I go ahead and take a look at my unit circle. I determine 150 degrees is going to be roughly here, and I think about my unit circle. That's going to be the point radical negative 3 over 2, comma, 1/2. So therefore, this equals plus or minus radical 1 minus radical 3 over 2, all divided by 2. Now, what we need to do to simplify this is I can think about this and think, I want to get rid of this fraction. We don't like having fractions, right? I hate fractions. Stop it with the fractions, right?
No, not really. So what we're going to do to get rid of the fractions is just multiply by your denominator. So I see my denominator here is 2, so I'm going to multiply the top and the bottom to keep my fraction equivalent. So I got to multiply everything by 2. So when I do that, I get plus or minus radical 2 minus radical 3 all over 4. Now what I can do is I can extract the square root of the denominator 4, and I can get my final answer is plus or minus 1/2, because the square root of 4 is 2, but it's still in the denominator, times 2 minus radical 3. And there you go. That's how you find the cosine, or the half angle of your cosine of 75 degrees.
Could we not have done like our other formula? And would you guys agree with me that 150 degrees plus 45 degrees is the same thing as tangent of 195? Is 150 give us a point that's on the unit circle? Does 45 degrees give us a point on the unit circle? So you could theoretically use the sum and difference angles, right? Correct? But that was from last homework, right? And I'm not asking you to use the sum and difference. I'm asking you to use the half angle formula. So what the half angle formula says, all right, if we're going to use tangent, then of u over 2 is equal to, half angle formula, first formula is cosine of u over the sine of u. OK. So it's saying you, for this, use that formula. Do you guys agree? Now, let's look at this formula. Tangent of u over 2 equals cosine of u. It's not saying u over 2, cosine of u over 2. Would you guys agree? It's not saying that. It's saying u over 2, and then that's u. So then 195 is equal to u over 2. So then, guys, for the formula, though, we need to figure out what u is. So how do we figure out what u is? Yeah, you got to solve for u. So you'd multiply by 2 on both sides. And you obtain 390. Ooh, 390 degrees. That is, it's a big angle, right? But let's think about really how big 390 degrees is. Well, we know all the way around a circle is 360. So how much farther we need to go to get to 390? 30. So 390 degrees and 30 degrees give you the same coordinate points on the unit circle. Would you guys agree? Yes? But it's a little bit easier just to use 30 degrees than 390. So when I'm doing this, I'm going to say that's equal to 1 minus the cosine of 30 degrees. I could do the cosine of 390 if I wanted to, but they're the same. They're going to give you the same point. So it's just much easier to use 30. And then I have sine of 30 degrees. Well, crap. What is the sine and cosine of 30 degrees? Here's 30 degrees. Knowing my unit circle, that coordinate point is 1/2 comma square root of 3 over 2. Would you guys agree with me based on your knowledge of the unit circle? John, good? Yes? Good. So then Marty will say that the cosine here is 1 minus 1/2 all over square root of 3 over 2. OK, let's look over here. Guys, do you agree with me that I have multiple little fractions here, right? I have a fraction inside of a fraction, right? Yes? So what did I do when I wanted to get rid of a fraction inside of a fraction? I multiplied by that little denominator. So over here, no, don't do it, don't do it. Over here, what should I multiply by? 2. And if I multiply by 2, on the top and the bottom, I now have 2 times 1, which is equal to 2. 2 times 1/2. I'm sorry, what happened in this? Huh?
That's 1 over square root. Or sorry, it's 1 over square root.
1 minus cosine of u. Cosine of that. Cosine is equal. Oh, well, I can just, I'm sorry. I can just subtract this, right? So why don't we just subtract that? Dang it, I did it again. I knew I was wrong. Thank you. Yes. Thank you. I didn't get the same answer last class, but I was like, what is going on? Yes, do not make that mistake like I did. I was thinking of pi over 3 again. 30 degrees is not pi over 3. 30 degrees is pi over 6, right? Thank you. I was like, this is not the same answer I had last class period. The answer is square root of 3 over 2, comma 1/2, right? Be careful when you're doing this. This is one of the more common mistakes people do. So just be very careful with that. So anyways, I did make a mistake there. This is 1 minus square root of 3 over 2 divided by 1/2. However, what should we do then? We should still do the same thing, right? I just had them switched up. So I'd multiply by 2 over 2. Thank you for that catch. Therefore, I get 2 minus the square root of 3 over 1. Which, ladies and gentlemen, is just 2 minus the square root of 3. OK?
OK, so what they want us to do for this problem is not to evaluate the sine of pi over 8 as u, but they want us to use the half angle formula. So the half angle formula states that sine of u divided by 2 equals plus or minus the radical of 1 minus cosine of u all divided by, not u, 2. So therefore, what we're saying is, in this problem, we have u divided by 2 is equal to pi over 8. So I say pi over 8 is equal to u divided by 2. So therefore, if I need to find the value of u to plug it in for cosine, I need to multiply by 2 on both sides, and I get pi over 4 equals u. Therefore, now what I can do is I'll plug this in. So sine of pi over 8 equals plus or minus radical 1 minus the cosine of pi over 4 divided by 2. So now what I need to do is evaluate for what is the cosine of pi over 4. Well, we go ahead and look at this. Take a look at our unit circle. Remember, pi over 4 is going to give us somewhere there. Radical 2 over 2, comma, radical 2 over 2. Therefore, the cosine is going to be a positive radical 2 over 2. So let's rewrite this. Plus or minus radical 1 minus radical 2 over 2, all divided by 2. Now, to kind of simplify this jumble, this looks ugly, right? So to simplify this, what I'm going to want to do is get rid of this fraction, the square root of 2 over 2. So to do that, I can multiply by 2. But remember, to keep your fraction equivalent, you're going to have to multiply the top and the bottom. And since this is an expression here, I have to make sure I multiply everything times 2. So therefore, what I get is plus or minus radical 2 minus radical 2 all over 4. Then what I can do is, this is the square root of everything. I can take the square root of my denominator. So that's going to equal plus or minus, the square root of 4 is 2, so I'll have 1/2 times 2 minus radical 2. And there you go. That's your answer. Find a half angle of sine of pi over 8.
What we've talked about for this is we could maybe break this up into the sum or difference formulas, right? We could possibly break that up into sum or difference formulas. Or what we could also do is break it up using half angle formulas. So if I was going to break this up into half angle formulas, then I could say that sine of 95 is equal to the sine of u over 2. And let's just try that. So if u over 2 is equal to 195 degrees, that means u is equal to 195 times 2, which ends up equaling 390. Now, can I evaluate on the unit circle 390 degrees? Well, let's do that. 360 is all the way around. How much more do I need to get to go to 390? 30 degrees. So in reality, I'm really just doing 30 degrees. Yes? Do you guys agree with me? So really, the reference angle in this case is really just 30 degrees. So if I want to use this half angle formula to evaluate, I need to use my formula. So it's plus or minus. Is it 1 minus cosine of u divided by 2 for sine? Yes. OK. Now remember I talked about the plus or minus. Here's where the plus or minus was going to kind of come in. now that if you guys look at what quadrant 195 degrees is on, 195 degrees is in the which quadrant? 195 degrees, not you. Third quadrant. Is sign positive or negative in the third quadrant? Negative. So your formula is going to be negative. Now, we just need to figure out the cosine of 30 degrees, which is going to be cosine of 30 degrees is going to be square root of 3 over 2. Okay? Now, again, guys, what I would prefer to do is get rid of my denominator 2. So what I'm going to do, Madison, is multiply everything on the top and the bottom by 2. By doing that, I get 2 minus the square root of 3 over 4, which I can break up into negative square root of 2 minus the square root of 3 all over the square root of 4. Can I now take the square root of 4? Yes. So my final answer would look just like that. It's a square root inside of a square root, and then divided it by 2. So if we're looking at cosine, kind of the same formula. However, which quadrant is 5 pi over 8 in? It's in the second quadrant. So when your half angle's in the second quadrant, for cosine, that means you're going to use the negative radical. Okay? So we have 5 pi over 8. Since that's in the second quadrant, cosine is going to be negative. And this would be 1 plus the cosine of theta. Well, if 5 pi over 8 is equal to theta over 2, then theta equals 10 pi over 8, which is 5 pi over 4. Do we know what the cosine of 5 pi over 4 is? Negative square root of 2 over 2. OK, good. So hopefully we'll brush up there on that unit circle for you guys. Again, you guys can see it's kind of the same process over and over again. That goes to a negative. Those divide out. Square root of 2 over 4. We can break that up and just rewrite that. Since I already did this once, we can rewrite that as a 2 in front. And then you guys can go from there.
So here we go. What I'd like to do is show you how to solve for the sine of 2x equals the negative square root of 3 divided by 2. We want to find all the solutions. So to first do this, what we want to do is find at least the solutions that are going to be on the interval of 0 and 2 pi. So again, I'll create my unit circle here. All right, so now what I want to do is determine, when are my values of my sine of an angle equal to negative square root of 3 over 2. Now remember that when looking at the unit circle, the sine of an angle is equal to the y-coordinate of that coordinate point of your angle on the unit circle. So I need to look over here and now determine that there's two angles that when my sine is equal to a negative square root of 3 over 2. Well, we can look at this and say it's going to be here and roughly here. All right, now that's not the best that you can look at this, but what I did is these are on my thirds. If I said 1/3, 2/3, 3/3, then this would be 4/3, 5/3, and then 6/3. So we're going to have, we could say x equals the angle. This first angle we're going to call is 4 pi over 3. And then the next angle is going to be 5 pi over 3. So we could say x equals 5 pi over 3 and x equals 4 pi over 3. So those are the two angles when I take the sine of an angle and it's equal to a negative square root of 3 divided by 2. However, we're not trying to find the angle of just x. It's actually 2x. All right, so then the next thing that we need to look at this is these are my two angles that are on the interval of 0 and 2 pi. But notice we want to find all the solutions. So we're going to keep on adding and subtracting our coterminal angles because we can keep on going around and around and keep on getting the solutions of sine being negative square root of 3 divided by 2, as long as we don't limit it between 0 and 2 pi. So to find my next angle, I can add 2 pi. And I can keep on doing this infinite many times, and so therefore I'm going to leave it as a variable n. Then I can also do the same thing with 2 pi n as well over here. So now to finally solve for x, what I'll do is I'll divide by 2 on both sides. And therefore my final solutions are going to be x equals 5 pi over 6 plus pi n, and x equals 4 pi divided by 6, which we can reduce to 2 pi over 3 plus pi n. So there you go, ladies and gentlemen. That's how you find all the solutions for a multiple angle. Thanks.
So in this last example, ladies and gentlemen, again, what we basically want to do, Jacob, is apply the inverse operations. Now, I don't need to do factoring for this one. This one's kind of like the last one. However, instead of my solutions being constrained between 0 and 2 pi, I'm going to find all real solutions. And I'll explain that once we get to it. However, first thing we want to do is let's just solve for, x, right? So I'll add 1 to both sides. Divide by 2. Oh, OK, yeah. Gotcha. Are we good? Take the square root. Now remember, when you're taking the square root, you have to include plus or minus, correct? Plus or minus. And then this is going to be 1 over the square root of 2. Rationalize the denominator. You get square root of 2 over 2. Does everybody see how I get my answer, square root of 2 over 2? Now, the answers, when you take it to square root, are plus or minus, correct? Plus or minus. Does everybody see that? That's huge, plus or minus. Because if I was going to look at my unit circle, which I'll do over here, we know that pi over 4 is pretty easy. Because it's the only one that is square root of 2 over 2, comma square root of 2 over 2. Right? However, is that the only time where we're going to have square root of 2 over 2? No, we basically have the angle over here. I'm going to erase this. You have this angle, and you have that angle. Do you guys agree with me? Those are all like my pi over 4s? Yes? It's OK. So all my reference angles are pi over 4. All the reference angles are pi over 4. Oh. There you go. Now, so I know that one of my solutions is x equals pi over 4. Correct? The next solution, well, we know halfway around a circle is pi over 4. So if I'm, or 4 pi over 4. So if I'm short one, then I'm at 3 pi over 4. Halfway around a circle is 4 pi over 4. If I go an extra pi over 4, I'm at 5 pi over 4. If all the way around the circle is 8 pi over 4, but I'm 1 short, then I'm at 7 pi over 4. OK, now here's where it's going to get difficult. Yes?
So are we looking at like the angles between each?
We're looking for all the angles where the sign is equal to either positive square root of 2 over 2 or negative square root of 2 over 2. And what I did is, once I found this angle, do you agree with me that if I reflected this coordinate point across the y-axis, the only thing that's going to change is the x-coordinate would be negative square root of 2, right? If I reflected over the y-axis, the point is exactly the same, except they're both negative. Do you see what I'm saying? So that gives you all the angles. Now, if my answer was between 0 and 2 pi, I would be done. That's what you do. Done. However, they're not asking for all the solutions between 0 and 2 pi. They're asking for all of the solutions. So what we need to kind of remember here is sine. What does sine look like? Here is between 0 and 2 pi. Correct? So basically, the first period is like the unit circle. But as you guys remember from graphing, sine goes on and on and on forever. It's never going to stop. So what that means is we need to write our solutions using a variable that can represent infinite many coterminal angles. Well, so here's how it kind of goes. And it's tricky and it's different for everyone. If here's my first answer, here's my first solution, right? Pi over 4. How far is it to my next solution? Be careful. How far is that? What is that distance? What is?
90 degrees.
That looks like 90 degrees, right? Isn't that pretty close to 90 degrees?
Yeah.
Which would be what in radians? Pi over 2. And then to get to the next answer, I'd have to do what? Pi over 2. Next one. Pi over 2. Next one. Pi over 2. Do you guys kind of see how this would keep on going?
Yeah.
Pi over 2. So therefore, instead of writing down all the answers, all I can simply do is start with one answer and say plus pi over 2 n. Remember how we wrote asymptotes with n? We're going to do the same thing. So if it's saying find all real solutions, a lot of times you're going to be using a multiplier n instead of just listing the answers. Okay?